Hello there, and welcome to Life Beyond Seen, where curiosity drifts as softly as the tide and science flows slow enough to dream by. Tonight, we're leaving the steady tick of clocks behind and diving into an ocean that hasn't existed for millions of years, one ruled by something both magnificent and terrifying. The ancient seas of the Miocene and Pliocene epochs were not the calm blue plains we imagine today. They were worlds alive with enormous creatures, layers of colour, and slow, deep rhythms that spoke to the heart of time itself. So, wherever you are right now, whether you can hear waves beyond your window or just the hum of a quiet room, I invite you to close your eyes and picture the horizon as it was when giants still moved through the deep. If you find this journey soothing or the science beneath it intriguing, a gentle like or a small tap on subscribe helps keep this tranquil corner of curiosity afloat for others who might need a calm voice before sleep. Now, let's drift beneath the surface, far back to an ocean thick with life and mystery, an ocean that belonged to the Megalodon. Imagine the world as it was roughly 20 million years ago. Continents were still on the slow march they've never stopped, but the arrangement of seas and shores looked familiar enough to orient you, and strange enough to unsettle you. The Atlantic was wide, the Pacific deeper, and the Indian Ocean shimmered under an atmosphere warmer than ours by several degrees. Ice had not yet gripped the poles completely. Vast tropical shallows stretched where today there is desert, and coral reefs rimmed entire coastlines like jeweled necklaces. The air carried more carbon dioxide, the winds were slower, and the rain fell heavy and often. It was an earth made for water, for creatures that thrived in endless blue. Down in those seas, sunlight reached farther than you'd expect. The upper layers were thick with plankton, the invisible grass of the ocean. Tiny, pulsing lives fed drifting clouds of fish that, in turn, fed creatures so large they redefined the meaning of presence. Whales were becoming true giants then, growing beyond anything that had ever swum before, and with them came predators that could challenge them. The Megalodon was one of those predators, the kind of being that rewrote the balance of the sea. Yet before it ruled, the ocean itself had to create the stage. Warm currents moved like highways, carrying nutrients and life across continents. The Indian Ocean flowed through the Tethys remnants, mingling with Atlantic waters that carried strange species eastward. It was a time of mixing, and wherever waters met, new life found ways to bloom. The ocean was not just alive at the surface, it throbbed with sound. Whales sang in lower tones, their calls carrying through entire basins. Schools of fish flashed in unison like thought given form. Giant turtles, each the size of a dining table, drifted through kelp forests as thick as jungles, and in the deeper channels beyond the reach of light, movements hinted at something massive and deliberate, an echo rather than a shape. The early humans who would one day fear the idea of sharks were still an unimaginable future away. Here, life obeyed nothing but the rhythm of current and hunger. To understand this ocean, it helps to strip away what we know now. Forget beaches filled with footprints and ships or nets or engines. There were no ports, no pollution, no hum of civilization. The seas smelled clean, sharp with salt, thick with organic scent. Storms could rise unchallenged, their winds sculpting waves that rolled for hundreds of miles before breaking on empty shores. Beneath them, the water temperature varied from bath warm near the equator to cool, dense flows that hugged the seabed and moved like the slow breath of the planet. Everything depended on that slow circulation. Oxygen, nutrients, temperature, and ultimately the life that would rise and fall within it. At night, the surface came alive with light. Bioluminescent plankton flickered with the same calm persistence as distant stars. To a creature like Megalodon, these glows mark the trails of smaller lives, signals of feeding and movement. In those same waters, early forms of dolphins chased squid that pulsed like firefly ribbons. Sea cows grazed in the shallows where mangroves dipped their roots into the salt, and penguin-like birds hunted in temperate zones, their wings turned to fins. The world was abundant. Every depth layer carried its own nation of life. And yet, as calm as it sounds from afar, that ocean was built on constant motion. The tectonic plates beneath it were reshaping coastlines that had stood for millions of years. When the Isthmus of Panama was still open, the Atlantic and Pacific exchanged waters freely. It created enormous swirling gyres that nourished plankton blooms large enough to alter climate. Later, when that passage began to close, global currents shifted and temperatures began to drop. But before the cooling, there was warmth, enough to let sharks grow beyond the size of buses and whales beyond buildings. The seas were not just big, they were generous. If you were to descend into that ocean, leaving the bright shallows behind, you would first notice how thick the life was. Shoals of mackerel and herring moved like clouds, dense enough to darken the light. Tuna larger than a human cut through them, followed by ancient relatives of swordfish, their long jaws gleaming with serrated edges. Further down, at the level where daylight fades into blue shadow, the temperature dropped a few degrees, and with it the mood shifted. The pressure became a weight you could almost feel in your teeth. This was the domain of slower predators, early sperm whales, giant squids, and broad-bodied sharks that navigated more by scent and vibration than by sight. Among them swam the early ancestors of the Megalodon, still large, still lethal, but not yet the perfected machines they would become. Their lineage stretched back to the Carcaricals genus, a line of sharks that had been evolving toward one goal: mastery of size. Evolution, in its quiet, persistent way, shaped them through success. Each generation that fed better, swam longer, or birthed larger young had an edge. Over time, edges sharpened into inevitabilities. By the height of its reign, the Megalodon would measure more than 50 feet from nose to tail and weigh as much as an entire pod of dolphins. Its teeth, triangular and serrated like steak knives, could crush bone with ease. But here, in the soft glow of prehistory, it was just another creature among many, one more participant in the grand experiment of the sea. To picture it properly, it helps to think not of the shark itself, but of what surrounded it. Imagine being suspended in open water, nothing but blue in every direction. The light falls in trembling columns, the surface above you a shifting mirror, below only depth. Somewhere in that expanse the faint tremor of movement, a pulse that travels through your chest before you even see it. That was how the smaller whales must have sensed the Megalodon, through pressure and vibration, long before the shadow took form. Even at rest, its presence changed the behaviour of the ocean around it. Schools would scatter, silence would settle, and the water would seem to hold its breath. But it wasn't always hunting. Like all large predators, the Megalodon's life was a balance between feeding, travelling, and resting. It patrolled coastal areas where whales migrated, waiting for calving seasons when young and slower individuals made easier prey. Fossil evidence suggests that many of its teeth are found in what were once warm, shallow nursery waters, suggesting it too gave birth close to shore. Those waters, calm and nutrient-rich, were the cradle of generations of giants. Young sharks the size of small boats would have spent their early months there, learning to move, feed, and sense the deep before venturing outward. And around them, the Miocene ocean pulsed with all the rhythms of a living system in perfect balance. Each current carried whispers of chemistry, carbon drawn down by plankton, oxygen rising from photosynthetic blooms, trace elements drifting from volcanic islands. The ocean was a network of flows. Remove one, and everything else shifted. It was a self-regulating engine, and during this warm period, it ran efficiently. The balance between predator and prey, between warm and cold, between shallow and deep, held steady enough to support giants. For the Megalodon, this meant endless opportunity. For the smaller lives, it meant an environment of constant vigilance. This soundscape would have been overwhelming to human senses. The low-frequency calls of baleen whales could travel thousands of miles. The snapping of crustaceans filled reefs with a constant crackle. Waves crashed against volcanic coasts. Thunder echoed through empty skies, and in between, the rhythmic thump of unseen tails drove pulses through the deep. Every movement sent a signature into the water, and every predator learned to read it. This was the ocean's language long before any human learned to listen. The surface, meanwhile, was a theatre of migration. Birds skimmed in arcs so low their wingtips brushed the water. Pods of dolphins churned in the wake of massive tuna runs. Even reptiles, survivors of an older world, had adapted to the sea's bounty. Sea snakes drifted in warm belts near the equator, while crocodiles ventured into saltwater deltas. And far out in the open, floating mats of sargassum created islands for crabs, eels, and the endless larvae of fish still too small to name. Everything moved. Everything was connected. To live in this ocean was to be part of a motion so vast it could never be fully seen. If you could hover above it, as satellites do now, you'd see the colour of the planet itself glowing deeper. More of the Earth's surface was covered in water then. The ice caps were smaller, the sea level higher, coastlines broader and more complex. The continents gleamed with wetlands and estuaries, and from above the sea would have seemed endless, an unbroken mirror of turquoise and cobalt, but beneath that calm surface life was a constant negotiation between hunger and survival, speed and stealth, warmth and depth. The Megalodon's ocean was both paradise and peril, and its rhythms shaped the fate of everything within it. As the sun set on that world, the colours deepened. Reds and golds burned across the waves before giving way to a steel-blue twilight. The surface quieted, but below, movement continued. The great migration of plankton began. Billions of tiny lives rising from the dark to feed under the moonlight. Following them came small fish, and behind those larger predators, each feeding on the one before. The pattern was ancient, unbroken, and beautiful in its simplicity. Above it all, drifting through the half-light, the silhouette of a shark so vast it seemed part of the sea itself. And this is where we begin to understand what kind of ocean could raise a creature like that. It wasn't just about size or strength. It was about stability, about a planet that gave its waters time to nurture and its creatures room to evolve. That ancient sea was a living archive, holding the memory of climates, the chemistry of volcanoes, and the rhythm of tides that would one day shape human coasts. The Megalodon's story is inseparable from that ocean story. They rose together, thrived together, and when the balance shifted, they fell together too. But for millions of years, under a warmer sun and across a wider sea, this world belonged entirely to the water, and somewhere, in that endless expanse, the slow glide of a shadow marked the beginning of an era when the ocean itself seemed alive with giants, and every wave carried the heartbeat of something immense. As we drift onward, the surface fades behind us, and the deeper story begins, not of a single creature, but of the ocean that made it possible. The ocean of the Miocene and Pliocene ages was a world that would have felt both familiar and profoundly alien. A planet that carried the same continents and the same blue skin as ours, yet arranged in ways that would have changed everything about how life moved and thrived. It was a time when the Earth was in the middle of a long, slow conversation with its own climate. The warmth of earlier epochs was beginning to ebb, but the ice caps were still hesitant things, small and uncertain, like ideas that had only just begun to form. The coastline stretched farther inland, seas flooded wide continental shelves, and shallow bays shimmered where deserts would one day lie. To trace a map of that lost ocean is to draw a portrait of motion, because everything, the land, the current, the temperature, the the creatures themselves, was in motion. The Miocene and Pliocene oceans were restless, shifting systems where evolution and environment danced in ways that would build giants like the Megalodon and later erase them just as completely. If you could have hovered above the planet then, high enough to see the curves of continents but low enough to feel the pull of the weather, you'd have seen oceans dominating the view. Nearly 75% of the surface was water, but not the uniform blue of satellite images. It was marbled with pale streaks where currents mixed, with the green and gold of plankton blooms tracing invisible winds beneath the surface. The Pacific was already immense, a deep basin that seemed endless even to creatures that would never see its edges. The Indian Ocean connected it to the warm shallows of the Tethys remnants, where Africa, Arabia and Asia pressed toward one another. The Atlantic was young, still stretching itself wider as the mid-ocean ridge pulsed like a heartbeat beneath the crust. These were not isolated worlds. They were a single, vast network of seas connected by passages that are now long closed. The Panama Seaway was open, letting water flow freely between the Atlantic and Pacific. Warm, salty currents looped through it, carrying nutrients, larvae and heat. This open door between oceans shaped everything from global temperatures to the diets of the largest predators. It was through these pathways that the ancestors of modern whales, dolphins and sharks spread across the world. The ocean's chemistry was different, and so was its mood. Carbon dioxide levels in the atmosphere were higher than today, which meant the oceans held more dissolved carbon, making them slightly more acidic but also more fertile. Microscopic algae thrived on that richness, turning sunlight and minerals into the foundation of life. The oxygen they released filled the water and the sky, while their tiny remains drifted to the bottom, building layers of chalk and limestone that still tell their story millions of years later. In some regions, the water was so thick with plankton that it coloured entire seas green, a visible living pigment that covered thousands of miles. These were the feeding grounds for small fish, which became the feeding grounds for bigger ones, in a cycle that spiralled upward until it touched the Megalodon itself. Every heartbeat of that shark was powered by the chemistry of those microscopic plants, though it would never know it. The temperatures of the sea were warmer overall. Near the equator, the surface might have reached 30 degrees Celsius, while even in higher latitudes the water stayed mild enough to invite life. Coral reefs expanded their reach north and south, building elaborate structures in places that are now far too cold for them. The Red Sea, for instance, was broader and deeper, an inland ocean lined with reefs and mangroves. The Mediterranean looked nothing like it does today. It was still connected, at times to the Atlantic, but occasionally isolated, its salinity rising until vast portions of it dried into salt flats. Farther west, the Caribbean was a vast open extension of the tropical Atlantic, filled with shallow lagoons and seagrass meadows where manatees grazed and turtles nested. It was a time of expansion, a kind of marine renaissance, when warmth and water conspired to produce an almost impossible abundance of life. But that abundance was not evenly spread. The great currents of the world, the conveyor belts of heat and nutrient, created regions of plenty and regions of emptiness. In the eastern Pacific, for example, upwelling zones drew cold, nutrient-rich water from the depths. These cold plumes fertilized the surface, feeding immense blooms of plankton that in turn supported whales, seals and sharks. The same process occurred off the coasts of what would become Peru, South Africa and California. These were the hunting grounds of giants. Megalodon teeth found along these coasts tell us that the species followed these fertile corridors, moving where the food was thickest. The fossil record is a kind of map in itself, each tooth a dropped pin marking where a hunter once patrolled. The distribution of those fossils outlines an empire that spanned nearly every warm ocean on Earth. The continents were moving too, closing gaps and forming new barriers. As Africa drifted northward and collided with Eurasia, it cut off the Tethys Sea, an ancient ocean that had once stretched from the Atlantic to the Pacific. Its disappearance changed the global circulation pattern, rerouting warm water northward and cooling some regions. The collision also lifted mountain ranges, which altered rainfall and wind patterns, feeding new rivers that poured sediment into the seas. Each of these shifts was subtle on a human scale, but enormous on an ecological one. When currents changed direction, migration routes changed. When coastlines rose or fell, breeding grounds appeared and vanished. The ocean was rewriting its own geography in slow, deliberate strokes, and every creature within it adapted or faded away. It's strange to think of time as geography, but in the ocean, it works that way. The Miocene Ocean was not the same at its beginning as at its end. 10 million years is a long time for currents to carve new paths, for sea levels to rise and fall by tens of metres, for climates to drift from humid to cool. The ocean of 15 million years ago was a warm, open world dominated by tropical waters. By the late Pliocene, the Earth had tilted closer toward the Ice Age rhythm that would define the next several million years. Glaciers began to expand in Antarctica. Sea levels dropped. The warm corridors that had once allowed species to travel freely began to close. The Megalodon, which had evolved in the Age of Openness, faced a future of barriers and cooling seas. If you trace a finger along the continental shelves of that era, you find clues to the shape of its life. Fossilized coral reefs mark the edges of ancient coastlines. Layers of sediment preserve the shells of plankton that once floated near the surface, their chemical signatures recording the temperature and chemistry of the water. Some of these records show sudden changes, brief pulses of warmth or cooling that would have rippled through the food chain. A single shift of a few degrees could move entire populations of fish hundreds of miles, could make once rich feeding grounds fall silent. And when prey moved, predators followed. The ocean was never still, never settled. The mammals of that time mirrored this restlessness. Early rorquals, the ancestors of modern blue and humpback whales, were beginning to evolve their filter feeding techniques. They roamed the high seas in herds, consuming the bounty of plankton that appeared with the upwelling seasons. Their size made them both unstoppable and vulnerable. To a megalodon, a juvenile whale was a perfect target, dense with energy and slow enough to catch. The relationship between these species shaped the very nature of marine life. The whales needed the plankton, the shark needed the whales. The plankton needed sunlight and minerals carried by currents. The currents needed wind and temperature differences created by the continent's positions. The whole web looped back on itself, everything depending on everything else. It was a balance that had taken millions of years to perfect, and that could be undone in the blink of a geological eye. Farther north, near the poles, life followed a different pattern. These were not barren regions even then. The Arctic and Antarctic circles were colder than the tropics, but still warmer than they are now. Sea ice formed seasonally but melted again in summer, allowing bursts of productivity that fed seals, penguins, and ancient relatives of polar bears. When icebergs calved and drifted into open water, they carried with them mineral-rich dust that fertilized vast stretches of ocean. It was another kind of migration, a slow one measured in months rather than miles, but it too left its mark on the food chain. These cycles of freezing and thawing, feeding and resting, were the early seeds of the polar ecosystems we know today, and they connected to the rest of the planet in ways that are still visible. The cold, dense water that sank at the poles helped drive global circulation, pulling warm water from the equator in return. Even the Megalodon's hunting grounds were influenced by those faraway drifts of ice. The sky above these seas would have been alive with wings. Great flocks of seabirds followed the same currents as the fish. Albatrosses soared for weeks without touching land. Pelicans, gulls, and early penguins nested on coasts that have since crumbled into the waves. The link between air and sea was as tight as the one between sea and land. The smell of salt and life carried for hundreds of miles. Storms gathered over warm water, spun themselves into hurricanes, and spent their force against the broad, shallow shelves of continents. Each storm stirred nutrients upward, resetting the cycle. Each calm that followed allowed life to bloom again. It was a living planet, its every movement a signal of renewal. In the shallows, the water was clear enough to see the bottom. Reefs spread like living cities, with corals building towers that housed thousands of species. Bright fish darted between sponges and sea fans. Crabs patrolled the sand, their shells gleaming like armour. Sea snakes and eels wove through the crevices, and in the distance the darker shapes of large predators cruised the edges of the reef, keeping the balance in check. Mangroves lined the coasts, their roots a maze for young fish and crustaceans. These nursery habitats were critical. Many species spent their early lives there before venturing into the open sea. Among them would have been the young of the Megalodon, born already large enough to avoid most threats but still small compared to what they would become. The survival of those young depended on the health of those shallow ecosystems. When later cooling and falling sea levels destroyed or altered these nurseries, it was another quiet step toward the decline of the giant shark. Looking at this ocean, it's tempting to think of it as paradise, but it was also a world of extremes. Volcanic islands rose and vanished within centuries. Earthquakes reshaped coastlines. The ocean floor itself was alive with vents that spewed mineral-rich water, creating oases in the darkness where strange creatures thrived without sunlight. The chemistry of these places hinted at the origins of life itself. Even in the age of giants, the smallest forms ruled the foundation. Bacteria processed sulfur and carbon, feeding worms, crabs, and fish that never saw the sun. The layers of the ocean, from the blinding surface to the eternal night of the abyss, were connected by invisible threads of energy and matter. Every drop was part of a greater machine. If someone could have drawn a map of this world, it would not look like any we know. Continents would be slightly displaced, their edges blurred by the high seas. The Panama Seaway would appear as a narrow blue ribbon connecting two mighty oceans. The Indonesian archipelago would be a maze of channels rather than a string of islands. Australia would sit closer to Antarctica, but still bask in tropical warmth. The outlines of Europe and Asia would merge into vast inland seas, and scattered across this watery expanse, the migration routes of whales and sharks would crisscross like invisible trade lines. It was a global network of life, fluid and dynamic without borders. This ocean, this blue planet of the Miocene and Pliocene, was the stage upon which the greatest marine predator of all time took its place. Its geography, its chemistry, its warmth and its motion all conspired to make such a creature possible. The Megalodon did not simply appear. It was born from the world that surrounded it. Every current that carried plankton, every reef that sheltered young fish, every whale that fed in the rich upwelling zones, all of them played a part in its story. To understand the shark, we must first understand the sea, and this was the sea that raised it. The map of lost oceans is not just a relic of geology. It's a memory of balance, of a planet that once gave more than it took, and of a time when the line between beauty and terror drifted quietly in the tide. The surface still glimmered under a sun slightly warmer than ours, and below, in that vast and fertile blue, the world was preparing for something immense to rise. The air above the Miocene seas carried a warmth that wrapped the world in gentleness, but beneath that comfort was a complexity that only the ocean could sustain. The Earth was running hotter than it does now, a few degrees on average, yet those degrees changed everything. They dictated where the currents moved, how the clouds gathered, and what kind of life the water could hold. The Megalodon's ocean was not simply a place of abundance by accident. It was the result of climate, chemistry, and motion working in quiet harmony. The steady breathing of a planet that had found a rare equilibrium. Every giant that swam in those waters, from the whales that filtered sunlight into flesh to the sharks that ruled the food chain, was shaped by that balance. To live as a giant required a world that could feed one, and in the Miocene and Pliocene, the planet was doing exactly that. The warmth of the period was born from a different arrangement of continents and oceans. Heat from the sun did not distribute evenly, but the wide seaways and open passages allowed it to spread farther than it does today. The Gulf Stream, which in our time carries warmth from the tropics to northern latitudes, had not yet been confined by the closing of the Panama Seaway. Instead, vast currents roamed freely between the Atlantic and Pacific, letting tropical water wash into cooler basins. This constant exchange blurred temperature boundaries and created a global ocean that was, in a sense, more unified. The equatorial zones were hot. The poles were mild and the gradients between them were gentle. That gentleness mattered. It made for calmer weather, fewer violent storms and more stable ecosystems. When wind patterns and water temperatures change too quickly, life struggles to keep up. In the age of the Megalodon, the pace of change was slow enough for life to adjust and flourish. Above the surface, the skies reflected that stability. Storms built slowly and with purpose. Clouds drifted in vast banks, born from evaporation that rose in shimmering sheets from the sea. Rain fell often but in steady rhythms, replenishing the rivers that carried minerals back to the ocean. It was a perfect loop. The warmth encouraged evaporation. The rainfall returned nutrients, and the rivers fed the coasts where life was richest. Volcanic islands dotted the tropics, each one a source of minerals and ash that seeded the surrounding waters. When those minerals met sunlight and carbon dioxide, the smallest life forms, phytoplankton, bloomed in staggering quantities. They were the quiet architects of abundance, invisible to the eye, yet responsible for the oxygen in the air and the carbon in the bones of every creature that swam above them. The chemistry of that ocean was finely tuned. With higher levels of atmospheric carbon dioxide, the water absorbed more carbon, but the temperature and alkalinity kept it in a form that still allowed shells and skeletons to grow. Calcium carbonate, the building material of corals and plankton, remained stable. The reefs continued to thrive, and the creatures that depended on them followed suit. Beneath the waves, the balance of gases was delicate but enduring. Dissolved oxygen levels fluctuated with depth and season, yet they rarely reached the hypoxic lows that plague modern coasts. The ocean breathed in long, slow cycles, each one taking centuries to complete. Cold water sank at the poles, drawing oxygen into the depths, while warm water rose at the equator, carrying nutrients to the surface. This was the quiet machinery of life. The thermohaline circulation, a global conveyor belt driven by differences in temperature and salinity. It was this movement that made the Miocene Sea a world of giants. The giants depended on that conveyor. Whales followed it across basins, moving from feeding to breeding grounds in patterns that mirrored the slow pulse of the currents. Sharks followed them, not by sight, but by instinct built from millions of years of inheritance. The same paths that carried warm water also carried the energy of the planet's metabolism. Iron, phosphorus, nitrogen and silica, all vital ingredients for plankton, flowed along those invisible routes. When a current met a continental shelf or an island chain, it was forced upward, and that upwelling brought nutrients from the deep. Each upwelling was like a heartbeat, creating oases of productivity where the water turned green and alive. Fish gathered there in clouds so thick they seemed to merge with the plankton themselves, and above them, predators gathered like weather fronts. This kind of abundance wasn't constant. It came in cycles. The Earth tilted slightly, wobbled on its axis, and its orbit stretched and tightened over tens of thousands of years. These subtle changes in the planet's position relative to the Sun, the Milankovitch cycles, altered the strength of seasons and the reach of currents. During warmer phases, ice at the poles melted back, raising sea levels and flooding coastal plains. New shallow seas formed, rich with sunlight and nutrients. When the cycle swung cooler, ice advanced, sea levels fell, and coastlines retreated. Life moved with those rhythms, never static but always adjusting. For a creature as vast as the Megalodon, whose range spanned oceans, these fluctuations meant constant migration. Yet, for millions of years, there was always somewhere to go, always another warm sea waiting beyond the horizon. The air chemistry mirrored the oceans. Carbon dioxide levels hovered around 350 to 450 parts per million, higher than in pre-industrial modern times, though not extreme. That greenhouse blanket kept the atmosphere moist and the nights mild. Forests thrived along coastlines and grasses spread inland, turning once dense jungles into open savannas. These land changes influenced the sea because every grain of soil carried to the ocean by rivers carried with it the record of the land's life. Iron from volcanic ash, nitrogen from decaying vegetation, and silicates from eroding rocks all ended up in the water. The sea was a mirror of the land, reflecting its chemistry and its changes. Where the land grew fertile, the ocean bloomed. Where the land dried, the sea grew lean. This constant feedback between air, land and water made the Miocene climate one of connected abundance. In those days, Antarctica was still a mosaic of ice and forest. The Southern Ocean circled it freely, a cold band that helped moderate global temperature. The northern polar region, by contrast, was almost temperate. Conifer forests grew along Arctic shores. The melting and freezing of polar ice influenced ocean salinity, which in turn shaped the great currents. When ice expanded, it locked away fresh water, leaving the seas slightly saltier and denser, strengthening the conveyor circulation. When it melted, the oceans freshened, slowing the currents and altering rainfall. Every living thing was connected to those patterns, even creatures that never saw the poles. The Megalodon, cruising through tropical shallows thousands of miles away, lived in a body of water whose temperature and chemistry were being dictated by ice it would never encounter. The entire planet was a single system breathing in and out over geological time. The weather that rolled across these seas was not violent in the way we imagine hurricanes today, but it was immense. Heat energy in the atmosphere meant that water vapor rose easily and condensed slowly. Storms could build over weeks, covering hundreds of miles. When they broke, the rain fell in thick, continuous sheets, and the runoff poured nutrients into the sea. The calm periods between these storms could last for months, allowing plankton to bloom in undisturbed layers. For the creatures that lived in the shallows, this meant cycles of feast and rest, of plenty and pause. Coral reefs grew rapidly in the warm, clear water, only to be pruned by occasional surges of sediment and wave action. They would recover, grow again, and repeat the cycle. The reefs were not fragile then. They were adaptable, accustomed to the gentle rhythm of disturbance and renewal. Deep beneath the waves, where sunlight faded into blue shadow, the chemistry of life took on a different character. Here, oxygen levels dropped, and the balance between decay and renewal decided the fate of ecosystems. The midwater layers, the twilight zones, were filled with suspended particles drifting slowly downward, the remains of plankton, tiny shells, bits of organic matter. This slow rain fed everything below. The deep-sea floor was covered in soft sediment, a continuous blanket of fine grains that recorded the passing of each season like rings in a tree. In this environment, even small changes in oxygen or temperature could shift the balance of species. But in the Miocene and Pliocene, the deep ocean remained relatively stable. It was a reservoir of cool, dark consistency that buffered the planet against sudden swings. That stability allowed large animals to roam widely, confident that wherever they went, the ocean would still sustain them. Chemically, the ocean of that time was almost a living laboratory. The ratio of oxygen isotopes in the shells of foraminifera, microscopic organisms that floated in the plankton, tells us that global temperatures were several degrees higher than now. Carbon isotopes reveal fluctuations tied to bursts of biological activity, times when carbon was drawn rapidly from the atmosphere into living tissue and then buried on the sea floor. These natural processes regulated the planet's climate long before humans existed to measure them. They were the slow dialogues of chemistry and biology, conducted through water instead of words. When the balance leaned toward more carbon in the sea, the Earth cooled slightly. When it leaned the other way, warmth returned. It was a self-correcting system, imperfect, but persistent. Every chemical reaction that took place in those waters was a quiet exchange of energy, but multiplied across the whole planet. They became weather. When plankton pulled carbon from the air, it changed the amount of sunlight trapped in the atmosphere. When whales and sharks migrated, they redistributed nutrients through their waste and their movement, stirring the layers of the sea. When storms stirred sediments, they released minerals that fed the next generation of life. There were no boundaries between biology and climate. Each was the other's reflection. The giants of that time were not separate from these processes. They were part of them. The megalodon's metabolism, its hunting patterns, even its growth rate were responses to the chemistry of the water it swam through. It lived within the breathing rhythm of the planet, and every bite it took was a product of 1,000 invisible chemical reactions happening all around it. As the Pliocene approached, subtle signs of change began to appear. Antarctica's ice grew thicker. The Panama Seaway narrowed, disrupting the exchange between the Pacific and Atlantic. Currents shifted, concentrating warm water in some regions and cooling others. The world was preparing for the long descent into glaciation, but for a time, the balance held. The Megalodon still reigned, the whales still migrated, the plankton still bloomed. The ocean had not yet crossed the threshold. It was still a blue planet designed for giants, held together by chemistry so stable it seemed eternal. And yet, even in its calmest days, the system was fragile in ways no creature could sense. The difference between a warm ocean and a cooling one can be measured in only a few degrees. For an animal the size of a city bus, that meant nothing at first. The water still felt the same. The prey still swam in abundance. The world still turned with predictable rhythm. But deep beneath the surface, in the quiet chemistry of the deep currents and the balance of carbon and oxygen, the changes had already begun. They would take millions of years to unfold, but they would end with the vanishing of the greatest shark the world had ever known. For now, though, the seas were still generous, the current still patient, and the air still warm enough to cradle a planet of giants. The Miocene and Pliocene oceans were immense kitchens where evolution cooked slowly, but with remarkable precision. Every current was an artery carrying food, every coastline a pantry filled with life in its rawest abundance. To exist in those waters was to be surrounded by motion and opportunity, because the ocean of that time was as close to perfect equilibrium as a living system could get. Nutrients rose from the depths in invisible rivers, plankton bloomed under the sun, and layer upon layer of creatures transformed that microscopic energy into muscle, bone, and instinct. The food chain was not a simple ladder, but a spiral that folded back on itself, an endless circulation of energy. Within that spiral swam the architects of fear, the first truly global predators, and at the centre of it all was the creature that would later be called Megalodon. But before that predator could exist, the ocean itself had to become a feast. Every element of the Miocene Sea was built on abundance. The foundation began with plankton, tiny cells turning sunlight into sugars and carbon into life. Their invisible bloom painted entire seas green, feeding small crustaceans and fish that swam through it in numbers so vast they appeared as clouds when seen from above. These fish, in turn, drew schools of larger ones, tuna, mackerel, and early forms of sardines. Whole species evolved to exploit these blooms, moving in great circular migrations that followed the invisible highways of nutrients rising from the deep. The result was a global rhythm of feast and scarcity that repeated with the seasons, pulsing through every level of the ecosystem. The predators learned those patterns just as surely as they learned the tides. At the higher levels of this chain, the ocean was alive with speed and teeth. The early Miocene had already seen the rise of apex hunters, great white ancestors, giant swordfish, massive marine reptiles that lingered from earlier ages. But as whales diversified, growing larger and more complex, the hunters followed suit. Size begot size. The baleen whales developed their filter-feeding systems capable of consuming tons of krill at a time. Their growth opened new ecological space, and evolution filled it with predators big enough to feed on them. That was the unwritten rule of the sea. Wherever life grew fat, something sharper appeared to eat it. The coastlines were nurseries of energy. Estuaries and mangrove swamps teemed with fish, shellfish, and smaller sharks. Warm, shallow water was the ideal breeding ground, and the gentle tides meant survival for the young of countless species. Crocodiles hunted here, their ranges extending far into salt water. Sea turtles nested on the beaches, their hatchlings spilling into the surf where seabirds wheeled and dove. The mix of salt and fresh water created gradients that fed microbial blooms, and those in turn supported everything above them. Each estuary was a miniature version of the larger ocean, an engine of recycling and birth. Farther offshore, the real powerhouses of productivity lay along the edges of continents. Upwelling zones, those regions where deep cold water surged upward, brought iron, phosphorus and nitrogen from the depths into sunlight. These elements fueled explosions of plankton and, by extension, everything that ate them. To a migrating whale, these regions were predictable refueling stops, the gas stations of the Miocene Ocean. To the predators that hunted them, they were banquets. Sharks, dolphins, and giant-toothed whales gathered in vast numbers where prey was thickest. Fossil evidence suggests that many of the largest predators of the time, including the Megalodon, concentrated their activity along these fertile coasts. The pattern was simple. Where the food gathered, the hunters followed. Among those hunters was a family of mammals that had turned the sea into their domain, the odontocetes, the toothed whales. They were the ocean's first intelligent killers, equipped with echolocation and complex social structures. Some, like the extinct Leviathan melville, rivaled the Megalodon in size and power. With skulls built for ramming and teeth the length of kitchen knives, they specialised in hunting other whales. The sea for a time was divided between two empires, one of bone and air-breathing mammals, and another of cartilage and cold-blooded precision. Their territories overlapped, their prey the same, their dominance contested. The encounters between Megalodon and those giant-toothed whales must have been monumental. Collisions of hunger and muscle on a scale almost beyond imagination. But the Megalodon did not rise overnight. It was the final product of a lineage that had been growing, generation after generation, into an apex form. Its ancestors, the Carcaricals and Otodus sharks, had spent millions of years refining their size and technique. Fossil teeth show the steady progression, each era producing slightly larger, sharper, more efficient specimens. The warm, nutrient-rich conditions of the Miocene gave them everything they needed: abundant prey, wide-open ranges, and stable temperatures that minimized energy loss. In such a world, size became an advantage without penalty. A larger body meant longer migrations, deeper dives, and the strength to take down massive prey. The physics of the ocean favored the colossal. The water supported the weight, the temperature preserved energy, and the food supply justified the effort. Evolution simply followed the logic written in the sea. Below the surface, the interactions between predator and prey formed a constant, invisible drama. Early dolphins swam in pods, their coordinated movements confusing smaller sharks. Baleen whales travelled in groups, protecting their young in the centre. Schools of fish moved in synchronized pulses, scattering and reforming like liquid metal at the first sign of danger. Every creature in that ocean carried strategies shaped by survival. Some relied on camouflage, blending into the dim light with mirrored scales. Others used speed, relying on bursts of motion that could outpace all but the fastest pursuers. But against the largest predators, even these tactics often failed. There were few defences against jaws 6 feet wide. The sound of this ocean would have been relentless. The clicks and songs of whales mixed with the thrum of swimming shoals and the low vibrations of giant predators cutting through water. The communication of prey became the soundtrack of their own risk. For the Megalodon, hearing was as vital as sight. Sound travels faster and farther in water, and it could detect the echoes of a distant whale from miles away. It did not need to chase constantly. It could wait, conserve energy, and move only when the signals converged into opportunity. Patience was part of its power. Every hunt began long before the strike, with awareness, timing, and the quiet certainty that everything in the sea was food eventually. To understand the scale of these ecosystems, picture the open Pacific during the peak of the Miocene. Across thousands of miles, massive filter feeders moved like slow-moving continents of flesh. Some were the size of modern whales, others smaller but in greater numbers. Around them, schools of fish followed the shadows for protection. Beneath them, sharks patrolled the dim half-light, tracing the movements of the herds above. When a whale weakened or a calf strayed, the sea erupted. A feeding frenzy in those waters would have been chaos. Water churning with motion, foam tinted red, dozens of predators converging in moments. Energy moved upward and downward through the chain in minutes, transferring from life to death and back again. This cycle defined the age. Everything depended on motion. Prey travelled along predictable routes, and predators learned them through instinct and experience. Fossils show concentrations of Megalodon teeth in regions that match ancient migration corridors of whales, particularly along what are now the coasts of North and South America, Africa and Japan. These were not random distributions. They were the echoes of repeated behaviour, of hunting grounds used for thousands of generations. The same bays that nurtured whale calves became ambush sites for sharks. The same deep channels that funneled plankton fed the food chain from bottom to top. The Megalodon's empire was a network of routes written into the shape of the earth itself. The smaller predators filled every niche beneath that giant. Makos and early great whites hunted mid-sized fish and seals. Smaller sharks like Hemipristis scavenged and cleaned the remains. Rays sifted the shallows for shellfish. It was a complete system, efficient and interconnected. Every kill fed something else. When a whale died, its sinking body became a feast for deep-sea life, a phenomenon still called a whalefall today. In the Miocene, those falls were more frequent and enormous. Crabs, worms and scavenger fish gathered around the carcass, feeding for decades. Even in death, the giants sustained the system that had sustained them. The chemistry of abundance was mirrored in the behaviour of predators. The Megalodon's strategy was not constant pursuit, but selective efficiency. It didn't need to hunt daily. A single whale could sustain it for weeks. Like modern sharks, it likely preferred high-fat prey, blubber-rich and slow. Its teeth, broad and serrated, were built not just for piercing but for shearing, cutting flesh cleanly from bone. A single bite could remove hundreds of pounds. Its jaw muscles, reconstructed from fossilized attachments, suggest a bite force far exceeding that of any living predator. It did not crush or tear randomly. It dismantled its prey with methodical precision. This was not the frenzy of a chaotic hunter, but the economy of a seasoned one. The ocean had given it everything, and it had learned to take exactly what it needed. The competition was fierce. Leviathan, the sperm whale with giant teeth, shared its domain and its diet. When two such predators met, the encounters must have been seismic. Their fights left no record but broken bones and scattered teeth, yet even those remnants tell of violence. Scratches and gouges on fossils show that such clashes happened. Whether one species consistently dominated the other remains uncertain, but the existence of both proves how fertile the seas were. two apex hunters of that magnitude can only coexist in an ecosystem of immense productivity. It was a world where energy flowed freely enough to feed titans without collapse. On the sea floor, scavengers waited for the leftovers of those titans. Hagfish, early crabs, and deep-sea sharks thrived on the refuse of the surface wars. Every drop of blood or flake of flesh that sank from above was used. The deep ocean was the recycling plant of the biosphere, turning death into new possibility. The chemical exchanges between surface and depth kept the water fertile. This balance, between birth and decay, between light and darkness, was the quiet foundation that allowed visible life to bloom so extravagantly above. Through it all, the climate still held steady. Warmth spread evenly across the globe, preventing major extinctions and allowing species to specialize. In such stability, complexity thrived. The reefs built towers, the whales grew larger, the sharks more refined. The arms race between predator and prey reached a level of sophistication unmatched before or since. Each improvement in defense, speed, schooling, or size invited an equal refinement in offense. Nature was engineering, patient and merciless. The Miocene Ocean at its height was not a place of still beauty, but a dynamic, living storm of interaction. Every motion had consequence. When a shoal of sardines fled a swordfish, it shifted the feeding pattern of an entire reef. When a whale migrated early or late, it altered the routes of predators that depended on it. The interconnectedness was absolute. The feast was never ending but never wasteful. Energy moved, always forward, always transforming. It was within this oceanic ballet that the Megalodon reached its peak. No other creature symbolized the culmination of that age so completely. Its existence was the sum of everything the Miocene Ocean had done right: its warmth, its fertility, its chemistry, and its motion. It was not just a shark, it was the ocean's logic made flesh. A creature that could only have existed when the world was generous enough to feed it, and stable enough to let it grow. The seas were vast enough for its migrations, the prey rich enough for its appetite, and the balance strong enough to endure its dominance. The Megalodon was the final word of that ecological conversation, a living signature written across the waves by millions of years of perfect, restless abundance. And as it swam through those glowing, plankton-fed waters, the feast continued to move around it. A living ocean, breathing, feeding, and endlessly reshaping itself into the world that would one day change. It is one thing to imagine the ancient ocean, it is another to picture what it created. Among the slow revolutions of current and chemistry, the Megalodon emerged not as an accident, but as an inevitability. The planet had built the perfect conditions for scale, and evolution had answered with precision. To meet this creature, even in imagination, is to encounter the result of every rule that governs life in water: how energy moves, how pressure shapes flesh, how hunger defines motion. The Megalodon was not just a shark. It was the architecture of predation rendered in muscle and cartilage. It was as if the ocean itself had decided to take form, to test the limits of what its warmth and abundance could sustain. The sheer physical presence of the Megalodon is almost beyond translation into modern experience. Estimates based on fossilized teeth and vertebrae suggest an average adult length of 15 to 18 meters, with some individuals possibly exceeding 20. That is the size of a modern city bus, longer than a telephone pole, heavier than a Boeing 737. Its mass may have reached 60 tons, a weight so great that gravity would have crushed it on land. Only the buoyant support of seawater could make such a body possible. Every movement of that bulk displaced tons of water, sending pressure waves ahead of it that smaller animals could sense long before the shadow appeared. To live in its proximity was to live inside the gravitational pull of its presence. Its shape was simple because simplicity works. The conical snout, the broad torpedo body, the tall sweeping tail, all of it built for efficiency. Unlike many prehistoric fish that carried ornamental fins or elongated spines, The Megalodon's form was stripped of excess. Evolution had honed it to the essentials of pursuit: power, endurance, and control. Its pectoral fins were proportionally larger than those of modern sharks, stabilizing its immense body in turns. The dorsal fin, rising like a tower above its back, may have reached 2 meters high, cutting through the water like the sail of a ship. The skin was armored in dermal denticles, tiny tooth-like scales that reduced drag and created microturbulence, allowing the shark to move silently despite its size. The smoother the skin, the quieter the hunt, and quiet was everything. Its teeth remain the most iconic evidence of its existence, and with good reason. Each one was a perfect instrument, triangular, serrated, and symmetrical. Some measured more than 17 centimeters from base to tip, the size of a human hand. They were designed not merely to pierce, but to shear. The serrations acted like saw blades, slicing through blubber, bone, and muscle in a single stroke. The jaws that held them formed a semicircle wide enough to swallow a small car. The bite force is estimated to have exceeded 10 tons, a pressure so immense it could crush the skull of a modern whale. Yet there was precision in that power. The Megalodon's jaws were not clumsy machines. They were articulated systems capable of fine control. The muscles attached to them were arranged for both explosive force and sustained clamping. When it bit, it could hold and shake, tearing massive chunks free while minimizing its own energy expenditure. Unlike land predators, which depend on speed over short bursts, marine hunters rely on strategy. The Megalodon could not afford to waste effort. Its metabolism, though slower than a mammal's, demanded immense caloric intake. A large whale could provide weeks of nourishment, but every hunt carried risk. The ocean is wide, and prey is mobile. The shark's advantage lay in patience and sensory awareness. Like all sharks, it possessed electroreception, an ability to detect the faint electrical signals of living muscle through specialized organs called ampullae of Lorenzini. In the Megalodon, these organs would have been extensive, allowing it to sense heartbeats even in murky water. It could feel the pulse of a swimming whale from hundreds of meters away. Its sense of smell was equally refined. Molecules of blood diluted to 1 part per 10 million could trigger a reaction, and the currents themselves carried the signals. To visualize how it moved is to imagine a paradox, immense yet graceful. Each stroke of its tail generated thrust through a motion called lift-based propulsion, where the tail's shape acted like an airplane wing. The water displaced downward lifted the shark forward, its speed sustained by the balance between buoyancy and gravity. At cruising pace, it likely travelled at 3 to 5 meters per second, but in attack, it could accelerate to nearly double that. Momentum was its weapon. The mass alone ensured that when it struck, the impact carried destructive force even before the teeth met flesh. A ramming blow to a whale's flank could stun or fracture bone. Once its prey was disabled, the shark circled, returning with surgical precision. Internally, its design was a study in optimization. Its skeleton, made entirely of cartilage rather than bone, was lighter and more flexible, allowing for sudden directional changes despite its size. Cartilage also repaired faster, an advantage in an environment filled with hazards. The liver, enormous and oil-rich, provided buoyancy and stored energy between meals. It also functioned as a chemical filter, helping regulate temperature. Sharks are not warm-blooded in the mammalian sense, but some species, including modern great whites, maintain partial endothermy, raising body temperature slightly above that of the surrounding water. This adaptation allows greater muscle efficiency and faster digestion. The Megalodon likely shared this trait, making it a warm water hunter capable of brief excursions into cooler regions when chasing migratory prey. The brain was small relative to its body, but the neural networks devoted to sensory input were vast. It did not think in concepts but in patterns, vibrations, scents, flashes of movement. Its intelligence was the intelligence of immediacy, honed by instinct rather than abstraction. Yet those instincts were extraordinarily refined. To navigate across oceans required spatial awareness beyond what most animals possess. It would have memorized temperature gradients, magnetic cues, and seasonal rhythms. Its migrations were likely predictable, but long, possibly spanning entire hemispheres. Some fossil evidence suggests that populations of Megalodon existed in every major ocean, except the coldest polar seas. It was not bound by region, only by opportunity. The life of a giant predator is not constant violence. For most of its existence, the Megalodon was a traveller. It would have spent days, even weeks, gliding through open water, conserving energy. It was solitary, except perhaps during mating or in rare congregations at feeding grounds. Its young were born live, as with most sharks, emerging already larger than most adult fish. Estimates suggest newborns reached lengths of 2 to 4 metres, longer than a human. These juveniles likely stayed near coastal nurseries, feeding on smaller prey until they could venture into the open sea. Fossilised teeth from juveniles are found in shallow marine sediments that were once warm lagoons. Those regions were the cradle of the species, where generations of giants began their quiet ascent into dominance. As it matured, the shark's role in the ecosystem became absolute. It regulated populations of whales and large fish, keeping the food chain balanced. Without such predators, smaller species could overpopulate, leading to collapses further down the chain. The Megalodon was the governor of abundance. Its presence ensured equilibrium, though unknowingly. Evolution does not plan. It simply balances through consequence. The shark was both destroyer and stabilizer, and the ocean beneath it functioned better for having such a creature in it. Its hunting technique was efficient to the point of elegance. Modern great whites attack from below, aiming for surprise, and the Megalodon likely used the same approach on a scale magnified 100-fold. Fossilised whale bones from the era show circular gouges matching the diameter of its jaws, concentrated around the chest and tail regions, locations where the shark could disable with a single bite. Once bitten, a whale would bleed rapidly, its movement slowing. The predator then waited, circling, conserving energy while its prey weakened. There was no need for prolonged struggle. The sea did the work. Buoyancy turned victims on their sides. The blood diffused into the water, and the current carried the scent outward. Lesser sharks and scavengers followed, but they only arrived after the giant had taken what it wanted. Despite its dominance, the Megalodon was not invincible. Its size limited its agility, and its need for vast amounts of food made it vulnerable to environmental change. The same traits that made it supreme also made it dependent. It was the apex form of an era defined by warmth and plenty, and when the climate cooled, that advantage became a burden. But in the time of its reign, it had no rival that could truly unseat it. Even the Leviathan, the great toothed whale, was rare by comparison. The Megalodon's reach was global, its adaptability unmatched. It could hunt in shallows, traverse the open ocean, and feed in deep pelagic zones. Few species have ever held such total command over their environment. Every fossilised tooth that humans unearth is a fragment of that dominance. Their enamel still gleams under light, their edges sharp despite millions of years in sediment. Each one is a record of both the predator and the prey it consumed, a symbol of an ecosystem at its peak efficiency. Holding one is to feel in miniature the precision of natural design. The serrations are symmetrical because symmetry cuts evenly. The base is thick because force must travel without fracture. The curvature is gentle because it must hold and release without locking. The perfection of the tooth mirrors the perfection of the creature that wielded it. The Megalodon was, in many ways, the ocean's final test of how large a predator could become before the system began to strain. It was the product of millions of years of incremental victories, the right mutation, the right prey, the right climate. Nothing about it was accidental. Its every feature was an answer to the question the ocean kept asking. How far can life go when energy is endless? The answer, for a brief and shining moment, was Megalodon. To see it would have been to witness motion stripped of effort. A massive body gliding in silence, the light breaking across its flanks in ribbons, the water parting in slow surrender. It was not monstrous in the moral sense humans attach to predators. It was simply the consequence of the sea's generosity. In its eyes, small, dark, unblinking, was no malice, only function. It ate because that was the language of survival. It swam because motion was the shape of life. It grew because the world allowed it to. The engine of this colossus was not rage or cruelty, but balance, the quiet, constant equilibrium of a planet that, for a while, made room for such perfection. And so it moved through its world, indifferent to everything but the signals of hunger and current, a creature that embodied the entire logic of the Miocene ocean. Its life was a translation of chemistry into motion, of abundance into scale. The Megalodon was the sum of its environment, an organism large enough to cast its own shadow across epochs. The water carried it forward, as it always had, toward the next unseen horizon of a world still bright, still warm, still full of a living breath beneath the waves. The ocean of the Miocene was not quiet, though to human ears it would have seemed still. Beneath that apparent calm was an orchestra of vibrations, whales calling in low tones that carried across entire basins, fish schooling in clouds that whispered against one another, the distant grinding of waves against volcanic rock. Yet amid all that sound, there was another kind of silence, the silence of a predator so perfectly adapted that its approach erased every trace of itself. The Megalodon did not need chaos to hunt. It relied on the ocean's own rhythms, folding itself into them until it became indistinguishable from the water that carried it. When it hunted, there was no roar, no flash, no warning. There was only motion, then absence, and the sea went on as though nothing had happened. To understand how it hunted, you must first imagine the environment not from above, but from inside the water. Light fades quickly there. Even a few dozen meters down, colour disappears, replaced by shades of blue and grey. Sound, however, travels 5 times faster than in air and can move across thousands of kilometres without losing strength. To a creature built for detection, the ocean is less a landscape of sight and more a world of pressure and pulse. Every fin beat, every flick of a tail, every heartbeat sends waves of energy through the water. The Megalodon lived in that invisible world, reading it the way a musician reads notes. It could sense the difference between a whale gliding, a fish darting, and a struggling calf calling to its mother. Its awareness was 3-dimensional, a constant field of information surrounding its body in all directions. When hunger called, the shark began its work long before the attack. It used its sense of smell first, because scent was the map of its world. Even a single drop of blood or a burst of organic matter could trigger the search. The ocean's currents carried those chemical trails like veins. The shark would swim slowly across them, zigzagging to find the concentration point, narrowing the gradient until the scent grew strong enough to confirm proximity. To the prey, there was nothing unusual about this movement. It was just one more shape passing in the distance. The shark's skin, covered in dermal denticles, minimized turbulence. The water slid past it with minimal noise. Its gills flared in slow, measured rhythm. Even the beat of its tail was muted, designed to generate thrust without cavitation. When the target was near, the shark began to read the water differently. Its electroreceptors came alive, detecting the minute electrical impulses generated by muscle contractions. The heart of a whale produces a field that can be sensed from hundreds of meters away. The Megalodon used that pulse like a beacon. It could determine direction and distance long before it saw its prey. Sight, when it came, was merely confirmation. Its eyes, adapted to low light, could detect movement even in the faint shimmer of the deep. But vision was secondary. In the realm where it hunted, sound and pressure ruled. The physics of its attack were built into its anatomy. Its body was a living weapon of hydrodynamic design. The head, broad and conical, reduced drag and focused energy forward. The tail, crescent-shaped and deeply forked, functioned like a double turbine, turning slow, heavy thrust into acceleration. The pectoral fins acted as stabilizers, giving it control at high speeds that smaller predators lacked. When the Megalodon chose to strike, the water itself became part of the weapon. It would dive deep beneath its target, using the darkness below as cover. Then, with a single burst of power, it would rise along a calculated vector, intercepting its prey from below or at an angle where visibility was lowest. Speed was not the only factor. It was timing. A whale calf swimming near the surface might never see the shadow below until the pressure wave hit. That wave alone could disorient, stunning the prey before contact. The impact that followed was an event of pure physics. A 60-ton body moving at even a few meters per second carried kinetic energy equivalent to an explosive blast. When the jaws opened, the lower half of the shark's head unhinged, widening the bite arc to nearly 3 meters. The teeth met flesh in a line of serrated steel, slicing through layers of blubber and muscle as though the material offered no resistance. The first strike rarely killed outright. It crippled. A severed fin, a broken rib, a torn artery, enough to rob the prey of mobility. Then the shark withdrew. It did not need to remain locked in combat. The ocean's currents and the prey's own blood loss would finish what the bite began. The Megalodon's senses tracked the chemical change in the water as its target weakened. The release of hemoglobin and other organic molecules created a trail that was as clear to the shark as smoke to a human eye. It circled at a distance, conserving energy. Smaller scavengers often arrived first, following the same signals. They were ignored. The giant had no competition worth noticing. When it returned, the water had already turned opaque with blood, the prey's struggle a series of fading convulsions. The shark would strike again only to feed, removing great slabs of tissue in careful, deliberate bites. Each movement was economical. Nothing was wasted. Its teeth, designed for efficiency, did not tear at random. The upper row sliced downward while the lower row gripped and stabilized. The serrations acted as microsaws, each stroke multiplying the cutting surface. When a tooth wore down or broke, another rotated forward from within the jaw. Sharks continuously shed and replaced teeth, and the Megalodon's jaws held multiple rows ready for deployment. Over its lifetime, it would lose and regrow tens of thousands, each one a record of its meals. Fossils show these teeth scattered across ancient seabeds, often near sites rich in whale remains, a trail of evidence marking where predator and prey once met. The actual bite mechanics were remarkable in both scale and precision. The muscle fibers responsible for closing the jaws were arranged in bundles along the skull, connecting to a joint system that distributed pressure evenly across the bite line. Unlike reptiles or mammals, sharks lack true jawbones. Their jaws are extensions of the skull, capable of independent motion. In the Megalodon, this structure acted like a hydraulic press. As the mouth closed, the muscles compressed cartilage plates that stored and released force in milliseconds. The result was a bite that combined crushing pressure with slicing speed. Modern biomechanical models estimate that the Megalodon could exert over 180,000 newtons of force, enough to bite through a car chassis. But the power of its bite was only half the equation. The other half was how it used that power. The shark targeted the points of structural weakness in its prey. Whale skeletons from the period showed damage concentrated around the thoracic region, where the ribs meet the spine, and the caudal peduncle, the base of the tail. These were deliberate strikes. A single bite to the thorax could collapse lungs and puncture the heart. A bite to the tail could immobilize, leaving the whale helpless in open water. Once its prey was disabled, the Megalodon could feed at its leisure. It was a strategy of control, not chaos. The shark didn't chase blindly. It calculated. Such precision required sensory awareness beyond the immediate. The Megalodon likely tracked prey migrations across thousands of kilometers, using temperature gradients and geomagnetic cues to navigate. It may have returned to specific feeding grounds annually, following the same cyclical abundance of whale calves or fish blooms. The shark's hunting calendar was written not in memory but in instinct, coded into its DNA by generations of successful hunters. It did not need to learn the ocean's geography. It was born knowing it, the same way birds are born with the map of their migrations embedded within them. The ocean's temperature shaped its behaviour further. Warm water allowed for greater metabolic efficiency, which meant longer bursts of speed. Cooler water slowed the heart, conserving oxygen during long glides. The Megalodon used this to its advantage, diving into deeper, colder layers to stalk and then rising into the warmth for attack. It exploited the thermal structure of the sea the way a pilot uses air currents. Even the physics of light worked in its favour. Approaching from below or from behind, the sun blinded prey temporarily, ensuring the first strike remained unseen. Its dominance was not simply physical but ecological. The presence of a megalodon in a region altered the behaviour of every creature around it. Schools of fish scattered at the faintest vibration. Smaller sharks avoided open water when the giants were near. Even whales may have developed early defensive formations in response to the constant threat. The patterns of life and death across entire coastlines were influenced by its roots. To the ocean's ecosystem, it was less an individual and more a moving boundary, a limit to be respected by all other life. When it fed, the aftermath became an event in itself. The leftover carcasses attracted scavengers from miles around. Crabs, smaller sharks, and fish stripped the remains, recycling nutrients back into the system. This feeding cascade sustained countless species. The Megalodon's kill was never just a meal. It was an ecological redistribution of energy. Its existence ensured the health of everything below it in the food web. The balance of the Miocene ocean depended on its appetite. There is a strange serenity in the thought of such violence conducted without malice. The hunt for the Megalodon was not a spectacle of fury but a ritual of precision. It moved when the water told it to move, struck when the signals aligned and withdrew when its work was done. The silence that followed each kill was not peace, it was equilibrium restored. Life continued, unaware of the calculation that had just unfolded within its midst. And yet, for all its power, the Megalodon's life was a constant negotiation between energy gained and energy spent. Its mass required constant sustenance, and every failure to secure a meal carried consequence. A single, missed migration season could mean starvation. Even perfection had limits. The ocean, generous though it was, remained an unpredictable partner. The currents shifted, prey moved, storms disrupted patterns. The Megalodon adapted, always moving, always reading the signs. That was its genius. Not intelligence in the human sense, but responsiveness. It existed in harmony with physics itself, obeying the simple laws that govern motion, density, and hunger. The silence of its approach, the precision of its strike, the unimaginable force of its bite. These were not just traits of a predator, but expressions of the ocean's own design. The Megalodon was the embodiment of what happens when the conditions of the world align so perfectly that efficiency becomes beauty. It hunted without drama, killed without hatred, and lived without waste. Every motion was justified, every kill necessary, every silence earned. The sea that built it was still warm then, still wide, still able to sustain giants. In those depths, time moved slowly, and the patterns of life seemed eternal. But even perfection carries the seed of its end, and the very forces that made the Megalodon unstoppable were already beginning to change beneath the waves. The Megalodon's ocean was too large and too rich to belong to a single ruler. Its dominance was immense, but it was never absolute. The sea it inherited was crowded with other giants. creatures born from the same warmth and abundance that had created it. The world of the Miocene and Pliocene was not a solitary empire of sharks, but a contested expanse where multiple lineages of titans thrived side by side, their coexistence shaped by a delicate balance of food, strategy, and adaptation. The Megalodon may have been the most formidable of them, yet it lived among rivals that tested its supremacy and neighbours that shared its vast, liquid realm. The ocean of that age was a parliament of giants, each holding dominion over its own ecological territory, each moulded by the same silent physics of survival. Across the Miocene seas, whales had already become architects of the deep. The early cetaceans of the Oligocene had been small, nimble predators, but by the time of the Megalodon, their descendants had transformed into the true masters of bulk and endurance. Baleen whales, the mysticetes, had evolved their elaborate filtering systems, replacing teeth with long plates of keratin that strained billions of krill and plankton from the water. They were the first herbivores of the oceanic world in a biological sense, animals that turned sunlight captured by microscopic plants into flesh on an enormous scale. Their growth changed the dynamics of the entire ecosystem. As they multiplied and increased in size, they became both stabilizers of the sea's productivity and the greatest source of energy any predator could ever desire. To the Megalodon, they were moving continents of food. A single adult baleen whale represented a feast so vast it could sustain even a giant shark for weeks. Fossil sites reveal the evidence. Teeth of Megalodon found alongside rib fragments and vertebrae of early Rorqual whales. The pattern of gouges tells a consistent story. Precision strikes near the chest and tail. The same strategy repeated across oceans. The predator had learned the weaknesses of its prey, and the prey had learned to live with the constant presence of a shadow it could never truly escape. Some whale species began giving birth in shallower coastal waters, where the massive shark's mobility was limited. Others formed loose groups, using numbers as deterrents. The relationship between the Megalodon and its whale prey was not just predation, it was co-evolution, a continuous shaping of body and behaviour on both sides of the equation. But whales were not only victims in this world. Some fought back and a few did so with equal ferocity. The Miocene and Pliocene seas hosted a predator that could meet the Megalodon in size and strength, Leviathan melville. This creature, named for its massive teeth, and the literary Leviathan that inspired its title, was a sperm whale built for war. It possessed a skull over 3 meters long and conical teeth nearly 30 centimeters in length, the largest of any known predator. Unlike modern sperm whales, which feed primarily on squid, Leviathan hunted other large marine animals, including whales and likely sharks. Its jaw muscles were anchored in a skull built for ramming, and its echolocation abilities gave it the precision of sonar-guided weaponry. If the Megalodon was the ultimate expression of the shark's evolutionary path, Leviathan was the apex of the mammalian one, a warm-blooded, social, intelligent killer that could match the shark's scale and cunning. Encounters between these two giants must have been rare, but when they occurred, they would have been cataclysmic. The shark ruled by stealth and ambush, the whale by strength and coordination. Leviathan could dive deeper and operate in colder water, giving it access to prey the shark could not easily reach. Yet in open tropical seas, the balance likely tipped toward the Megalodon. Its range was wider, its endurance greater in the heat, and its energy expenditure lower. The fossil record leaves no definitive evidence of direct conflict, but bite marks on whale bones and the overlapping distribution of their remains suggest a period of competition. They occupied the same food pyramid, each feeding on the same energy source, whales smaller than themselves. Evolution rarely allows two top predators to dominate the same niche indefinitely. Sooner or later, one yields. Whether Leviathan declined first due to climate change or competition remains uncertain, but by the late Pliocene it had disappeared. For a brief epoch, however, the two shared the same sea, each testing the limits of predatory design. Beyond Leviathan, other whales played more subtle roles in this theatre of giants. Early ancestors of modern orcas, small social odontocetes, began experimenting with cooperative hunting. They learned to surround schools of fish or corner smaller whales, dividing labour within the pod. This social intelligence, though still in primitive form, marked a turning point in marine evolution. Intelligence had begun to compete with size. While the Megalodon relied on solitary power, these proto-orcas relied on strategy and communication. Over millions of years, such cooperation would prove more adaptable to a changing world than even the most perfected physical form. The Megalodon's neighbours extended far beyond whales. Giant sea turtles, some exceeding 3 meters in length, drifted across tropical currents. They were not prey for a shark of its size, too small to justify the effort, but they shared its highways and nurseries. Dugongs and sea cows grazed in the shallows, descendants of land mammals that had taken to the sea. Seals and walrus-like pinnipeds began populating the temperate coasts, their bodies evolving thicker layers of fat to withstand cooler waters. These creatures introduced new dynamics to the food web, serving as both competition and collateral. The Megalodon's diet was broad. It would have consumed anything large enough to offer substantial reward. Yet the ocean's productivity meant it rarely needed to waste energy on smaller fare. Reptilian holdovers from earlier ages still lingered as well. Crocodiles extended their ranges into coastal marine environments, particularly along the warmer shores of Africa and South America. One, Purosaurus, grew to lengths exceeding 12 meters, though it remained bound to estuaries and river deltas. These animals were no threat to the Megalodon, but their presence emphasized how fertile the world remained, an age when gigantism was not exception but norm. Everything that the Earth's warmth touched seemed to grow large. The great filter feeders of the open sea, the whales and their kin, shaped the behaviour of every predator around them. The Megalodon's migrations mirrored theirs, a dance repeated over eons. When whale populations moved south for breeding, the sharks followed. When they returned north to feed, the predators were already waiting. Fossil concentrations along ancient continental shelves reveal a recurring pattern of nursery grounds, for both species overlapping geographically. It was not coincidence. It was the geometry of ecology, drawn by instinct rather than intent. The leviathans were not the Megalodon's only competitors. The oceans of that era were also home to large macroraptorial dolphins such as Zygophyzeta and Acrophyseta, smaller relatives of Leviathan that hunted cooperatively or in pairs. They targeted medium-sized prey and occasionally scavenged on kills left by larger predators. Their intelligence gave them flexibility, though their size confined them to narrower ranges. Along continental margins, early ancestors of modern great white sharks, Carcharodon hastalis, were rising. Sleeker, faster, and adapted for cooler water, they occupied a niche that the Megalodon's immense body could not, hunting smaller prey in regions beyond the giant's tolerance. When the Earth's temperature later dropped, these descendants would inherit the seas the Megalodon left behind. The coexistence of all these giants did not mean constant conflict. The ocean was large enough to allow them separation. Spatial and dietary partitioning reduced overlap. One predator fed on deep-diving prey, another on surface dwellers, another on calves or carcasses. The balance held because the environment could support it. The Miocene was a time of vast productivity, where the currents of nutrients were so strong that even the presence of multiple apex predators did not cause collapse. It was a rare equilibrium, a biological detente that would last millions of years. For smaller creatures, these giants were both terror and benefactor. Whale falls created deep-sea ecosystems that fed generations of scavengers. Shark kills redistributed nutrients along coasts. Even the decaying carcass of a predator became a miniature world, sustaining crabs, worms, and fish for decades. In this way, the giants maintained the very systems that allowed them to exist. Death fed life, life fed death, and the ocean never stopped turning over its energy. To move among these beings would have been to witness a scale of life difficult to grasp now. A pod of early baleen whales stretching for kilometres, their exhalations rising in rhythmic plumes. A Leviathan breaking the surface with a tail strike that echoed across miles. A Megalodon's dorsal fin slicing the water near a shoal of dolphins, sending them scattering into the distance. Each creature held a presence that shaped the water around it, bending sound, pressure, and even light in ways that smaller life could sense but never see. The ocean was a web of giants communicating through motion alone. Even the seabirds that patrolled the skies above were larger than those of today. Giant petrels, albatrosses, and shearwaters traced the same currents, feeding on fish driven upward by whales. To them, the Megalodon's hunts were events to be followed from above, the surface boiling with activity, the spoils of deep death rising in slicks of oil and blood. For every kill that happened below, hundreds of creatures benefited above. Nothing in this ecosystem existed in isolation. Among these rivals and neighbours, the Megalodon was neither villain nor anomaly. It was simply the most efficient design in a world of abundance. Its presence did not erase other giants. It coexisted with them because the sea could afford to sustain all of them. But the same forces that allowed this coexistence also contained its undoing. The equilibrium depended on warmth, on a stable chemistry that kept the conveyor belts of nutrients moving. When the climate began to cool, even slightly, the chain started to falter. The whales adapted through migration and social intelligence. The smaller predators adapted through flexibility. The Megalodon, built for a world of constancy and scale, found itself in a shifting system where energy became more unevenly distributed. Its rivals, or their descendants, would survive by being smaller, faster, or smarter. The age of giants was beginning to wane, yet for that long span of millions of years, the ocean was home to a congregation of titans unmatched before or since. The Megalodon swam among equals, and the sea itself seemed built to hold them. Its neighbours were not enemies, its rivals not constant threats, but fellow expressions of an era when life on Earth reached outward into every possible dimension of size and strength. To imagine them all together, the shark, the whales, the toothed leviathans, is to glimpse a world of scale almost divine in its balance. The waves above them may have looked calm, but beneath, an empire of giants moved through the blue, each pulse of their motion reminding the planet what it was capable of creating when energy and time conspired in harmony. The coasts of the Miocene and Pliocene were not boundaries between land and sea so much as corridors of life, broad and luminous, where everything living seemed to gather at least once in its existence. They were worlds within worlds, filled with sound and movement, cradling the beginnings of entire species. Warm water rolled over coral shelves that glowed in the sunlight. Mangrove roots tangled like veins, and quiet lagoons reflected a sky heavy with the scent of salt and decay. It was here, in the shallow warmth where the tide met the river and the sea folded into the land, that the story of the Megalodon began, and that the ocean itself maintained its endless renewal. These were the nurseries of the ancient world, the places where life rehearsed its survival before returning to the open water. The continental shelves of that era stretched far beyond the modern coasts, because sea level stood higher, the ice caps still small and hesitant. Entire regions that are now dry land lay beneath shallow, sunlit seas. The light reached down through meters of clear water, igniting reefs that sprawled for hundreds of kilometers. The coral systems of the Miocene were vast engineering projects of biology, cities built from calcium and time. Each coral polyp, no larger than a pinhead, extracted minerals from the water to form exoskeletons that would outlast the creatures themselves. Generations layered upon one another, building walls, arches and towers that reached upward toward the sun. These structures sheltered a living multitude. Fish wove through the passages in schools that shimmered like liquid metal. Crustaceans hid in crevices, their shells blending with the rock. Sponges, anemones, and soft corals filtered water constantly, turning the ocean itself into a breathing organism. Every square meter of reef was a competition for light, food, and space, and yet everything existed in balance. The coral reefs were the planet's laboratories of evolution. Species diversified here faster than anywhere else. Every new shape of fin, every novel pattern of movement was tested against the shifting demands of the environment. The predators that rule the open sea were born indirectly from these shallow places. The small fish that learned to move in coordinated schools became the ancestors of the great pelagic shoals. The rays that evolved flat bodies to hide from reef predators became masters of camouflage in open sand. Even the sharks began here. Juveniles, newly born and still vulnerable, used the complex architecture of the reefs as cover from larger hunters. Fossil deposits in ancient coastal sediments reveal concentrations of juvenile Megalodon teeth, evidence that these places served as safe havens for their earlier stages of life. The mangrove forests behind the reefs were the next line in this web of abundance. Their tangled roots formed walls that trapped sediment and slowed the tide. The water there was murky, warm and rich with organic matter. Fallen leaves decomposed into nutrients that fed plankton blooms, which in turn fed small fish and crustaceans. These were the feeding grounds for countless juveniles, including the young of large sharks. The mixture of salt and fresh water created gradients of salinity that few predators could tolerate for long, making the mangroves a natural refuge. Here the young megalodons grew in relative safety, their diet consisting of rays, smaller sharks, and bony fish. The abundance of food and protection allowed them to grow rapidly until they could venture into deeper water. Above these mangroves, the skies were dense with life. Seabirds nested in branches that dipped into the water, dropping fish remains that fertilized the soil. Insects hovered in clouds, and reptiles basked on exposed roots. The entire system functioned as a biological filter, converting the detritus of the land into the foundation of marine productivity. When floods came, they carried nutrients from rivers into these estuaries, fueling the next cycle of growth. It was an endless exchange between land and sea, the kind of subtle continuity that modern coastlines have mostly lost. The mangroves of the Miocene were the lungs of the shallow ocean, breathing out oxygen and breathing in decay. Beyond the mangroves, sandy bays stretched out where rivers met the sea. These bays were nurseries of another kind, open, sunlit, and filled with gentle waves. Seagrass meadows spread across the shallow floor, forming dense carpets that anchored sediment and slowed currents. The grass itself hosted entire ecosystems. Tiny snails grazed on its leaves, shrimp and crabs moved among its blades, and young fish found food and shelter in its labyrinth. When seen from above, these meadows looked like emerald continents beneath the surface, waving softly in the tide. Their importance to marine life cannot be overstated. They provided food for herbivores, refuge for the young, and oxygen for the surrounding waters. Without them, the abundance of the Miocene seas could not have existed. The soundscape of these coasts would have been constant. Waves broke softly against the reefs. The crackle of shrimp echoed through the shallows, and the distant calls of dolphins carried from deeper water. Schools of fish moved through the shallows in shifting patterns that mirrored the flicker of sunlight on the surface. Rays stirred the sand in spirals, leaving behind ghostly imprints. In the early morning, the water was often still, and one could see the silhouettes of larger creatures beyond the reef, juvenile sharks perhaps, or turtles drifting lazily between feeding grounds. These coasts were never empty. Life was not an exception here. It was the default state of being. The productivity of the reefs and mangroves influenced everything that lived beyond them. Nutrients from decaying coral, seagrass and detritus flowed outward, carried by tides into the open ocean. This constant export of energy fueled plankton blooms far offshore, linking the shallow and deep ecosystems into one continuous chain. The Megalodon's world depended on that connection. Without the abundance of the coasts, the pelagic food webs could not sustain their higher tiers. Each giant predator, each whale, each swarm of krill owed its existence to the quiet, unnoticed work of coral and mangrove. Among the predators that haunted the shallows were smaller sharks, relatives of the megalodon that fed on the juveniles of other species. Species like Carcharhinus and Hemipristis ruled these regions, patrolling the edges of reefs where open water began. Their presence kept populations in check, preventing overgrazing of the seagrass and overpopulation of small fish. Even here, in what seemed like peace, balance was enforced by teeth. The megalodon's young grew among these hunters, learning by instinct to move silently, to detect vibrations in the water, and to avoid silhouettes overhead. By the time they reached maturity, their bodies had already learned the geometry of survival. The reef systems themselves changed over time, shifting with sea levels and tectonic motion. As continents moved and climates fluctuated, coral communities adapted. In some regions, the reefs grew upward, following the retreating light as sea levels dropped. In others, they drowned under rising water, forming limestone foundations that would one day become fossilized cliffs. The pattern of these changes can still be read in the rock record. Fossilized coral beds stretching across modern mountain ranges that were once shallow seas. They are silent witnesses to an age when the Earth's warmth allowed coral to reach latitudes now far too cold for them. In those days, the reef stretched across the entire tropics in nearly unbroken continuity. From the western Pacific to the Caribbean, chains of coral connected the continents. The Tethys remnant still shimmered as enclosed seas between Africa, Asia and Europe, their shallow floors glowing with reefs. These interconnected habitats allowed species to spread easily. Fish that evolved in one region could colonize another within a few generations, carried by larvae drifting on currents. This mobility kept ecosystems diverse and resilient. Genetic variation was constant, adaptation immediate. The result was an explosion of life unmatched in scale. The mangrove coasts acted as stabilizers during storms. Their roots held the soil, and their canopies broke the force of waves. During heavy rainfall, they absorbed excess water, releasing it slowly back into the sea. In this way, they protected both land and ocean from disruption. They were nature's infrastructure, ancient and efficient. Every flood, every cyclone, every surge of tide passed through them and emerged as renewal rather than destruction. The coastlines of that time were not fragile margins, but living systems that absorbed and redistributed energy. At the higher reaches of the estuaries, where fresh water mixed more strongly with salt, freshwater fish and amphibians thrived. Some species crossed these zones seasonally, feeding in brackish water before returning inland. The connection between terrestrial and marine ecosystems was seamless. The remains of land plants washed into the ocean and became the first step in the food chain for marine life. Everything flowed toward the sea, and everything the sea produced eventually returned to the land through the air and the rain. The young megalodons born in these coasts lived in a world that seemed infinite. They grew among the coral towers, learning to move through confined spaces with the precision that would one day make them masters of open water. They hunted small fish among mangrove roots, tested their strength against rays, and felt the pull of the tides that led to the wider world. Their survival rate was low. Most fell to other predators before reaching full size, but those that did survive carried the lessons of the coast into the deep. Every megalodon that later cruised through the vast ocean had once been a small, cautious hunter hare, shaped by the geometry of reef and root. As the epochs progressed, these coastal ecosystems evolved into even more complex systems. New coral species appeared, better adapted to temperature fluctuations. The mangroves expanded farther inland, colonizing new delta systems, but slowly the rhythm began to shift. Subtle, cooling trends altered the chemistry of the water. Some coral species began to bleach and die in shallower regions, while others migrated toward the equator. The balance of salinity and temperature that had once been perfect started to waver. Yet for millions of years these coasts endured. Their productivity continued to feed the ocean's giants, long after the first signs of climatic decline had begun. If the open sea was the domain of power, the coasts were the domain of continuity. Every generation of life began here, in the quiet shallows. The reefs were the architects of form, the mangroves the engineers of stability, and the bays the caretakers of growth. Together they sustained a cycle so perfect that it could support the largest creatures that would ever live. The abundance of the Miocene was not a miracle. It was the logical result of an Earth that knew how to feed itself. The Megalodon's empire may have stretched across oceans, but its foundation was built in places no deeper than a human could stand. A few meters of warm, breathing water where coral, sand and root conspired to create eternity. The open ocean of the Miocene and Pliocene was not an empty wilderness. It was a landscape without borders, a continuous and living expanse that stretched beyond the limits of sight, filled with travellers that never truly stopped moving. Everything alive in those waters migrated, whether it was a single plankton drifting with the currents, or a whale crossing hemispheres in pursuit of warmth and food. The surface shimmered with sunlight during the day, but by night it transformed into a vast illuminated plain of bioluminescence, the glow of millions of organisms marking invisible routes through the dark. These were the pelagic highways, the arteries of the planet's living ocean, where life flowed endlessly in motion, feeding, breeding, and dying in patterns that repeated over millions of years. The great ocean currents that defined the Miocene world were the scaffolding of this movement. They were not random, chaotic drifts, but structured systems driven by temperature, salinity, and wind. The equatorial countercurrents, the North and South Pacific gyres, the circumpolar flows of the Southern Ocean, all of them carried heat, nutrients, and life across vast distances. Warm tropical water moved poleward, cold water sank and returned along the deep conveyor. These movements created invisible corridors that shaped everything from weather to evolution. The creatures of that age followed them not by knowledge but by inheritance. The megalodon, the whales, the schools of fish, and the flocks of seabirds above were all linked to these same circulating paths. A whale calf born in the Miocene tropics would have learned the rhythm of migration as its first lesson. Its mother led it along the ancient routes that connected breeding grounds to feeding zones, the paths lined by upwellings where plankton rose in dense spirals. The whales moved in slow convoys, their massive bodies rising and falling in perfect timing with the ocean's breath. Each exhalation broke the surface with a sound like thunder, echoing across miles of open water. Below them, the megalodon travelled the same routes, silent and patient, using the faint vibrations of the whales' songs as beacons. It followed them across oceans, not in pursuit of a single hunt, but in synchronization with the movement of its entire prey base. In the vast mid-ocean regions where land was nothing but memory, these creatures met along the same highways again and again. Schools of tuna, mackerel, and sardines shimmered in the upper layers, feeding on the seasonal plankton blooms. Their movements were choreographed by the seasons, following the shifting line of sunlight as the planet tilted on its axis. Where they went, the hunters followed. Swordfish, dolphins, and smaller sharks darting in flashes of silver and shadow. Far below, squid pulsed upward at night to feed on the same prey, rising through the twilight zone in vertical migrations that connected the deep to the surface. The megalodon's world was alive not just in the horizontal expanse of the sea, but in the vertical space from light to darkness. At dusk, the ocean changed its character completely. As the sun dipped, the surface cooled, and an unseen migration began. Billions of microscopic creatures, plankton, copepods, small fish, rose from the depths to feed in the cover of night. This nightly ascent, the largest migration on Earth, brought the deep to the surface. The water shimmered faintly with bioluminescence, tiny points of light flashing whenever something disturbed the surface. To a megalodon gliding through that darkness, the light was a map of motion. It could sense where the plankton clouds gathered, where the fish followed, and where the whales came to feed. The open water night was never still. It was a living galaxy, the stars replaced by the glow of life itself. The megalodon's own migrations followed the logic of the planet's seasons. Warm currents drew it toward temperate coasts in summer, where whales bred and food was plentiful. As autumn cooled the water, it followed the retreating herds toward the tropics. Fossil evidence from multiple continents shows clusters of megalodon teeth that correspond to these migration paths, especially along what are now the coasts of California, Peru, South Africa, and Japan. These were the highways of giants, routes passed down through generations. The same regions that nurtured whale calves also nurtured shark offspring. For both predator and prey, the ocean was a cycle of departure and return. Whales were the sound of this ocean. Their songs, low and resonant, rolled through the water for hundreds of miles. In the absence of human-made noise, the sea carried their voices clearly, forming a network of sound that connected individuals across entire basins. The whales' communication was both practical and social, navigation, mating, reunion, but it also served as a kind of atmospheric texture for everything else living in that ocean. Sharks like the Megalodon, though not musical themselves, moved within that soundscape, their senses attuned to its vibrations. Every note of a whale's call was also a signal of proximity, a vibration that could betray location and intent. Above, the seabirds traced their own highways in the air, following the same routes as the currents below. They nested on islands and seamounts, using the wind to travel thousands of kilometers. When the whales breached or the tuna shoals surfaced, the birds descended in waves, feeding on scraps. From above, they could see what no creature below could, the faint, glowing outlines of the ocean's hidden geography. Even without continents to guide them, they followed the same invisible structures, the eddies, the convergence zones, the plankton fronts that marked where the deep ocean met the surface world. The pelagic ecosystem of that age was bound by motion, but motion required energy, and energy required structure. The upwelling zones served as the great engines of life. Along continental margins and island chains, deep water rose, rich with nutrients drawn from ancient sediments. Iron, phosphorus, and nitrates surged upward, feeding blooms of diatoms and algae that painted the sea in swirls of green. These were the true factories of abundance. From the plankton that multiplied there came everything else: the krill, the fish, the whales, the predators that followed them, and finally the megalodon that hunted them all. The open ocean was vast, but its productivity was concentrated along these narrow highways of motion. A mature megalodon travelling along such a route would have moved with measured grace, conserving energy during its long migration. It did not need to feed constantly. One successful hunt could sustain it for weeks. It likely swam deep during the day where the water was cooler and denser, rising only at dusk when the whales and fish gathered nearer the surface. Its path was guided by instinct reinforced through generations, a biological memory of temperature gradients, salinity, and magnetic cues. These were the same cues used by whales, turtles, and even the smallest fish, all tuned to the same planetary rhythms. The night in the open ocean was an ecosystem of light. Every disturbance produced a cascade of blue-green sparks. The movement of a single shark sent ripples of light radiating outward, fading as quickly as they appeared. Whales breaking the surface to breathe carried trails of glowing plankton on their skin. Schools of squid flashed in bursts, signalling to one another in silent pulses. To witness it would have been to see the sea transformed into a universe of living stars. For the Megalodon, it was simply home, a realm where visibility came not from sunlight but from the living energy of the water itself. These highways were not permanent. Ocean circulation shifted with the slow dance of continents. As the Isthmus of Panama began to rise toward the end of the Pliocene, the connection between the Atlantic and Pacific narrowed. Warm equatorial currents that once flowed freely were disrupted, forcing the oceans to reorganize. The Atlantic grew saltier, the Pacific cooler. The currents that had linked the world's ecosystems for millions of years began to change course. Migration routes that had once been open for generations grew more difficult. Some feeding grounds became barren, others overcrowded. The stability that had allowed the great ocean wanderers to thrive was beginning to erode, but during its height the Miocene Sea was still an endless plain of opportunity. The Megalodon's path crossed those of whales and dolphins, sea turtles and seabirds, squid and fish. Every creature, large or small, moved through the same fabric of currents and temperature, bound together by the same invisible laws. Their migrations overlapped, intertwined, and sustained one another. There was no stillness, no true separation between any point in that ocean. Life flowed like a continuous current, self-renewing, self-balancing. The whales sang, the sharks followed, and the ocean carried them both. Even in its quietest moments, the water was alive with meaning. The songs of whales may have served as acoustic landmarks, sonic beacons that helped others navigate across the endless blue. When the sound faded, the magnetic field of the earth itself guided them, a whisper beneath the noise of waves. The ocean's navigation system was as ancient as the planet, embedded in every living cell that crossed its depths. In the deep layers below the surface, the rhythm of migration continued unseen. The twilight zone, where sunlight barely penetrated, hosted creatures that drifted upward and downward in cycles longer than a day. Lanternfish, small but numerous, formed columns that stretched for hundreds of meters. At dusk they ascended to feed. At dawn they sank again into safety. Predators like the Megalodon may have used these migrations as cues, following the daily movement of biomass through the water column. The deep, cool layers acted as highways of their own, connecting the ecosystems of the abyss to those of the surface. The open ocean at night was a theatre of persistence. Every life depended on another, every movement echoed through the water as both signal and risk. There were no hiding places, only distance and motion. The predators hunted not out of choice but necessity, and the prey moved constantly to survive. It was a dance as old as the planet, repeated with each turn of the earth. For the Megalodon, these highways were not just routes of travel, they were the structure of existence itself. Its entire life unfolded along them, from the moment it left the safety of coastal nurseries to the years spent roaming between hemispheres in search of prey. It followed the same invisible corridors as its ancestors, guided by forces older than its species. Every migration, every hunt, every return to warmer waters was part of the same unbroken pattern. The open ocean night continued, silent and eternal. The glow faded and returned with the motion of the sea. The currents never ceased, the whales never stopped singing, and the giants kept moving along their endless blue roads. The planet, in its perfect balance, still breathed through them. For now, the highways remained open, and the ocean still belonged to the wanderers. Below the surface brightness of the Miocene Ocean, where sunlight lost its strength and colour drained from the water, there existed another world, one that almost never saw light, yet pulsed with its own quiet intensity. The surface may have belonged to motion and spectacle, but the deep, the true abyss, belonged to stillness and endurance. It was a place where energy arrived not as sunlight, but as slow rain, the continuous drift of dead plankton, fecal pellets, and tiny fragments of life descending from the upper layers. This was the world beneath the highways, a realm the Megalodon visited only in passing, but one that underpinned everything above. The dark below was both graveyard and cradle, the final resting place of the ocean's giants, and the birthplace of entire ecosystems built from their remains. The transition into this world was gradual. At a few hundred meters, the light dimmed into blue haze. At 1,000, it was gone. The temperature fell, the pressure increased, and the world became one of perpetual night. The creatures that lived here were adapted to scarcity. Their bodies were gelatinous, their metabolism slow, their senses tuned to faint vibrations or chemical traces. Tiny crustaceans and worms sifted through the falling snow of organic matter that drifted down from above. Each particle was precious, a speck of sunlight transformed by the chain of life into sustenance for the unseen. The twilight zone, where the last hints of light lingered, was already populated by small predators and drifting fish, but below that, in the midnight zone, life shifted into something stranger, an existence defined by patience. The Megalodon rarely ventured this deep. Its massive body was designed for warmer, higher layers, where prey was abundant and oxygen plentiful. But the traces of its presence could reach even here. When one of its kills, a whale or large marine mammal, sank beyond the reach of scavengers near the surface, it entered a slow descent that could take hours. The body spiraled downward, tumbling weightless in the cold, trailing a plume of fading blood and oil. Around it gathered smaller sharks and hagfish, stripping away the soft tissues as it fell. Even in death, the giants fed the deep. By the time the carcass reached the sea floor, much of its bulk was gone, but what remained, bones rich in lipids and collagen, became the foundation of a new community. This was the phenomenon that scientists would later call a whale fall, but in the Miocene, it was simply part of the ocean's daily rhythm. When a whale's remains touched the bottom, they were instantly colonized. Crabs, amphipods, and deep-sea isopods arrived first, devouring the remaining flesh. Within weeks, the bones themselves became host to a bloom of bacteria that thrived on the lipids locked within. These bacteria formed mats, releasing sulfides into the surrounding sediment. The chemical transformation created by their metabolism attracted entirely new species: worms that fed on the sulfur, mussels that farmed symbiotic microbes, and creatures that never needed sunlight to survive. Over decades, these communities evolved using the energy of decay rather than the energy of the sun. In this way, the deep ocean sustained itself on the memory of surface life. The whale fall was a microcosm of the planet's entire logic. Nothing wasted, everything transformed. In the absence of light, chemical energy ruled. Cold seeps, natural vents on the seafloor that released methane and hydrogen sulfide, created similar oases in the abyss. Here too, life clustered in improbable abundance. Tube worms grew meters long, nourished by internal bacteria that processed the chemicals. Clams, crabs, and even fish adapted to the toxic environment, finding ways to extract sustenance from the Earth's internal breath. These seeps dotted the continental slopes like underwater gardens, their presence often marked by the gleam of white bacterial mats spread across the sediment. They were silent, patient factories of life, fueled not by sunlight but by geology. In the dark, time moved differently. The deep ocean had no seasons, no day or night, no weather to speak of. Change came in centuries, not minutes. The currents that swept the bottom were slow but constant, redistributing sediments and oxygen. Each particle that settled on the seafloor might remain undisturbed for thousands of years before being moved again. The creatures that lived there were built to match that rhythm. Some deep-sea fish lived for decades. Some corals, growing in the black stillness, survived for millennia. Everything that thrived here did so by conserving energy, by doing less rather than more. Evolution, in the abyss, was a study in restraint, and yet the deep ocean was not entirely isolated. The cycles above, the blooms of plankton, the migrations of whales, the deaths of giants, were all connected to it through the rain of organic matter. Each storm at the surface sent pulses of nutrients downward. Each year's migration ended in new layers of sediment. The Megalodon, by feeding at the top of the food chain, indirectly nourished the bottom. The carbon locked in the bodies of its prey sank into the abyss, where it would remain for millions of years, stored in the cold and dark. The deep was the ocean's memory, holding the record of everything that lived and died above. The pressure here defied comprehension. At a depth of 4,000 meters, every square inch of surface bore the weight of hundreds of atmospheres. Metal would crush, bone would collapse. But the life built for that world had no need for rigidity. Soft bodies bent rather than broke. Fluids replaced structure. Some creatures produced internal antifreeze, keeping their cells from freezing solid in the near-zero water. Others generated light to communicate or hunt. The deep sea glowed in its own quiet way, small flashes and pulses marking the presence of predators and prey, in a realm where the only constant was darkness. Among the most haunting sights in this world were the remains of the great whales themselves. Over time, their bones became coated in sediment, fossilizing slowly as minerals replaced calcium. Some remained partially exposed for centuries, forming skeletal monuments on the seabed. Around them, bacteria and worms continued their work, turning even stone-hard remains into sustenance. In a sense, the deep ocean was the final recycler of the planet, ensuring that nothing of value ever truly vanished. The cycle of energy that began with sunlight at the surface ended here, in chemical reactions powered by decay. For creatures like the Megalodon, the deep remained both mystery and boundary. It was aware of its presence, perhaps sensing the pressure drop when diving after injured prey, but it did not belong there. The cold stole its energy. The darkness limited its senses. It was a creature of motion, built for the living light of the upper sea. The deep was too still, too slow, a place where even time seemed to hesitate. Yet the Megalodon depended on it as much as any abyssal worm did. Without the deep's capacity to absorb and recycle carbon, the surface world would have drowned in its own excess. The abyss regulated life by transforming death. The architecture of the deep ocean floor in that era was far from featureless. Continental slopes descended into wide plains where fine sediments accumulated over millions of years. Beyond them rose seamounts and ridges, volcanic remnants covered in thin films of manganese and iron. These hard surfaces provided anchorage for corals, sponges, and other sessile life. The ridges themselves served as highways for bottom currents, carrying nutrients laterally across basins. Occasionally, submarine landslides triggered by earthquakes reshaped these landscapes in minutes, burying entire ecosystems beneath new layers of silt. The deep was not immutable. It changed slowly most of the time, but when it moved with catastrophic force. Cold seeps and hydrothermal vents punctuated the monotony of the abyss with life's defiant brilliance. At the vents, where water superheated by magma erupted through cracks, plumes of minerals fanned out into the blackness. Metal deposits formed shimmering chimneys, and within their toxic clouds thrived colonies of organisms found nowhere else on Earth. Though these vents were rare and isolated, they represented continuity with the planet's earliest history, the same chemical reactions that might have birthed life itself billions of years earlier. The deep was ancient in every sense, a window into both the beginning and the end of living matter. The silence here was total, broken only by the slow creak of settling sediment or the faint tremor of distant tectonic activity. Sound, when it came, was magnified by the density of the water. The groan of icebergs calving far above, the muffled thunder of underwater quakes, the songs of whales travelling downward until even the abyss could hear them. These sounds gave the deep a strange intimacy, connecting it to events thousands of kilometres away. Nothing in the ocean was truly separate. Everything resonated through the same liquid medium. The deep ocean during the age of the Megalodon was as much a part of its story as the sunlit shallows. though it existed in near total darkness. Every life that fed the shark, every whale it brought down, eventually became a contribution to this unseen world. The abyss was the final partner in the exchange, the place that received what the upper world released. Its stillness was not absence but accumulation. It gathered time the way reefs gathered light. When we think of those ancient seas now, it's easy to imagine them only in colour and motion, the greens of the shallows, the silver of fish, the blue expanse of the pelagic zones. But the true heart of that ocean lay in the black below, where the energy of sunlight ended and the energy of decay began. The deep ocean was the other half of life, the mirror that absorbed everything the surface created. It was the keeper of the balance, ensuring that the abundance above did not destroy itself. The Megalodon's shadow may never have reached these depths, but its legacy did. Every bite, every hunt, every kill it made sent echoes downward in the form of sinking matter, feeding unseen millions. The abyss received those offerings without judgment, turning them slowly into stone, then into the chemical whispers that sustained its own hidden citizens. Life in the deep needed no witness. It was its own audience, its own reward. The dark below remained eternal, indifferent to the dramas above. It accepted the fallen giants, digested their remains, and waited patiently for the next generation to join them. Even as the climate above shifted and the world began its long cooling, the abyss stayed nearly unchanged, a steady heartbeat beneath the planet's transformation. It was the place where everything ended and everything began again, a silence so complete that it might as well have been the ocean thinking to itself. The change began quietly. There was no single catastrophe, no sudden extinction that shattered the seas. Instead, the transformation came as a slow and a patient rearrangement of the world's breath. The warmth that had sustained the Miocine's vast abundance began to fade degree by degree, across centuries that stretched into millions of years. The air cooled. The water followed. The currents that had once moved freely across oceans began to falter and twist into new patterns. What had once been a blue planet of stability became a shifting mosaic of boundaries, and for the giants who depended on the constant generosity of the sea, that change would be their undoing. The Megalodon, built for a warm, wide and steady ocean, found itself in a world that was learning to grow cold. The great conveyor belts of the ocean, the systems of circulation that distributed heat and nutrients, were the first to feel the strain. For millions of years, the open seaways between continents had allowed warm water to flow unimpeded, keeping global temperatures balanced. But as the Isthmus of Panama rose from the depths and finally sealed the link between the Atlantic and Pacific, that equilibrium ended. The Atlantic began to hold more salt, its currents intensifying and looping northward. The Pacific, deprived of that exchange, cooled. The winds shifted. Monsoons weakened in some places and grew violent in others. The great gyres that had once been highways of life became barriers. Entire species that had drifted freely between oceans found themselves isolated. Isolation is the first step toward change, and change does not favour giants. The Megalodon's reach depended on open water and on the constant migration of prey. Its life was a cycle of movement, following whales that in turn followed plankton, that in turn followed sunlight and current. When the connections between those systems broke, the shark's empire began to fracture. The whales it depended on started to alter their routes. Some turned toward colder regions where plankton thrived in the nutrient-rich upwellings created by new patterns of circulation. The Megalodon, tied to warmer seas, could not follow them indefinitely. Its physiology demanded heat. It could venture into cooler water for a time, but not for long enough to sustain its way of life. The balance between energy gained and energy lost began to shift against it. The cooling of the earth was not uniform. It came in waves, pulses that alternated between warmth and decline. Each pulse left its mark in the layers of ocean sediment and ice. The story of a planet settling into the rhythm of ice ages. Glaciers advanced and retreated at the poles. Sea levels fell, exposing continental shelves and shrinking the shallow nurseries that had sheltered generations of young sharks. The coral reefs that had once stretched like luminous chains across the tropics began to contract. Mangroves retreated inland, their delicate roots unable to withstand the colder tides. The shallows, the birthplaces of abundance, were disappearing. For the Megalodon, reproduction had always depended on these coastal havens. Its pups, though born large, were still vulnerable to larger predators. The warm, protected lagoons had given them the space to grow before venturing into the open sea. But as the global climate cooled and sea levels dropped, those lagoons vanished one by one. The coastlines became rougher, more unstable, often too cold to serve as nurseries. The young were forced into deeper, riskier waters where survival rates plummeted. The species could no longer replace itself as quickly as before. What had been a stable cycle for millions of years began to break down. The prey that once filled the seas changed too. The warm water whales that had once been slow and heavy began to give way to more agile species adapted to colder environments. Rorquals, ancestors of modern blue and humpback whales, developed new feeding strategies that allowed them to travel farther and eat more efficiently. They followed the blooms of krill into colder waters, places the Megalodon could not comfortably survive. Even their birthing ground shifted toward higher latitudes. The energy of the ocean was moving poleward, leaving the tropics comparatively barren. The Megalodon's range shrank like a tightening circle. As its world cooled, competition intensified. Smaller, faster sharks began to multiply in the new conditions. The early great white Carcharodon carcharius evolved from the same lineage that had produced the Megalodon's ancestors, but took a different path. Leaner, more efficient, better suited to hunting in cooler, nutrient-rich waters. These sharks required less food, could reproduce more frequently, and tolerated a broader range of temperatures. They thrived where the Megalodon could not. In the fossil record, the overlap between their teeth marks the turning point, the moment when one design began to replace another. It was not a battle of dominance, but a shift in advantage. The ocean's new logic favoured versatility over mass. Even the chemistry of the sea turned against the giants. As ice accumulated at the poles, the balance of carbon and oxygen shifted. Cooler water absorbed more carbon dioxide from the atmosphere, altering the pH and slightly reducing the availability of the minerals that many organisms depended on. Plankton communities changed in composition. The types of prey that had once dominated the food chain, large, fatty fish and warm water cetaceans, became less common. The entire structure of the marine ecosystem began to simplify, trading size for speed, specialization for flexibility. For a creature like the Megalodon, whose life relied on the uppermost tiers of that system, the decline of complexity meant the slow collapse of its world. The process was invisible from moment to moment. No single year or generation would have sensed it clearly. The ocean still teemed with life, and the Megalodon still hunted, still fed, still swam along the ancient routes. But with each century the balance tilted further. Its hunts grew longer, its meals less frequent. The energy it spent chasing prey across fragmented oceans began to outweigh what it gained. The margins of survival thinned. The young that did survive to adulthood found themselves in emptier seas, chasing fewer whales through colder currents. The abundance that had once defined the world was dissolving into scarcity. The cooling also brought the return of new predators and scavengers from the edges of the ecosystem. Orcas, the intelligent hunters that would one day inherit the role of apex predator, began to appear in recognizable form. They were smaller than the Megalodon, but far more adaptable, able to coordinate hunts and exploit prey in ways the solitary shark could not. They worked in groups, attacking from multiple angles, exhausting their victims with strategy rather than brute strength. The The shift from solitary to social predation was one of the ocean's great evolutionary turning points. The Megalodon's strength was immense, but it was fixed. The orca's advantage was intelligence, and intelligence could change faster than climate. Meanwhile, the whales themselves adapted to the changing seas. Baleen species developed migratory behaviours that allowed them to exploit seasonal productivity at high latitudes and then return to warmer waters to breed. The pattern of abundance that had once been evenly distributed across the globe became concentrated in narrow bands near the poles. The Megalodon's immense body required consistency, but the world no longer offered it. To survive in a patchwork ocean meant constant travel, and constant travel meant exhaustion. The very size that had once been its greatest asset now became its burden. The geological timeline of extinction is blurred. The fossil record shows the Megalodon's presence waning gradually between 3.6 and 2.6 million years ago, vanishing entirely as the Pleistocene ice ages began. There was no cataclysm, no final event, only the slow fade of a lineage that could not adapt quickly enough. Its disappearance coincides with the rise of the first large-scale glaciations, when the poles locked in ice and sea levels dropped by more than 100 metres. The shallow seas that had once served as breeding grounds were gone. The open ocean had grown colder, less fertile, less forgiving. The last of the giants likely died in waters that had once been home to their ancestors, their bodies sinking into the same abyss that had fed their world for millions of years. Yet extinction is never just an ending. It is a reorganization. The disappearance of the Megalodon opened ecological space for others. The great whites spread into new territories. Orcas and other toothed whales diversified. The balance of the ocean reset itself. The world that followed was leaner, more dynamic, shaped by cycles of ice and melt that rewarded adaptability over magnitude. The age of warmth and excess gave way to an age of endurance. The Megalodon became a ghost within that transition, a relic of a world that no longer existed. Even as the giant disappeared, its influence lingered. The evolutionary arms race it had fueled left marks on its prey and competitors alike. Whales grew faster and more agile. Sharks evolved new strategies of ambush and cooperation. The legacy of its predation echoed through species that never knew its presence. The shape of the modern ocean still carries its fingerprint in the behaviours of those who came after. The instinctive fear that drives whales to gather in groups, the patterns of migration that trace ancient roots, even the hierarchy of modern marine predators, all of it is the echo of the age of the Megalodon. The planet itself, as if exhausted by its own abundance, settled into rhythm again. Ice advanced from the poles, reflecting sunlight, cooling the air. Deserts formed inland as the climate dried. The lush coasts that had once been nurseries turned to rocky shorelines. Coral reefs retreated to narrower belts around the equator. The tropical seas that had once supported empires of life became fewer and farther between. The energy of the earth had been redistributed, and with that redistribution came the end of the great experiment in gigantism that had defined the Miocene. The ocean, though changed, endured. It always does. The Megalodon's extinction was not the ocean's failure, but its adjustment. The system corrected itself, rebalancing the ratio of predator to prey, energy to consumption. The giants had played their part. Their disappearance allowed new forms to flourish. Evolution does not mourn. It simply continues. The great shark, once the embodiment of power and abundance, became part of the sediment, its bones and teeth scattered across the seafloor, waiting for a future intelligence to find them and wonder at what the world once was. If there was a final generation, it would not have known its own ending. The water would still have carried the same soft blue light, the same smell of salt, the same slow rhythm of wave and current. The last Megalodon would have swum as its ancestors did, patient, deliberate, unaware that its kind was fading from the earth. In its final moments, it would still have been what it had always been. The embodiment of balance between hunger and grace, a creature built perfectly for a world that no longer existed. And when it died, sinking slowly into the cold, the deep would have received it as it had received all things, folding it into the endless memory of the ocean. The cooling seas moved on, the giants vanished, and in their place rose a new order of survivors, smaller, quicker, more cunning. The age of warmth had ended, but the story of life continued, written now in leaner lines, its abundance tempered by restraint. Yet beneath every wave, in the chemistry of the water and the rhythm of its movement, the echo of that vanished world remained, a reminder that even the greatest forms of life are only temporary arrangements of energy, shaped by the earth, sustained by balance, and erased by the same hand that created them. What remains of the age of the Megalodon is silence made visible, teeth mostly, enormous, triangular, serrated relics scattered across the beds of ancient seas now turned to stone, each one a fragment of a jaw that no longer exists, a trace of something that once shaped the rhythm of entire oceans. They are smooth now, polished by time, their edges dulled by sand and water. When you hold one in your hand, you hold a piece of the planet's memory. It is heavy, not just in weight, but in implication. This tooth once sat in the mouth of a creature longer than a bus, heavier than any animal that has ever lived on land, and yet what remains of it fits easily into the palm of your hand. The fossil record of the Megalodon is not a story of violence, though it comes from a world of predation. It is a story of scale, of how large life once dared to grow when the earth was generous. The fossil beds where these teeth are found form a quiet network of the past. From North America's eastern seaboard to the coast of Peru, from the warm sediments of South Africa to the cliffs of southern Europe, the Megalodon left its trace like a signature written across the continents. Most of the remains come from the shallow deposits of ancient coastal seas, places that were once breeding grounds or feeding corridors. The bones of whales often accompany them, scored and punctured with the unmistakable marks of serrated jaws. Each site tells the same story repeated across millions of years, an ocean full of motion, hunger and abundance. But the fossils themselves are calm, stripped of all that movement. In stone, even the ferocity of the hunt becomes geometry, the clean angle of a tooth, the curvature of a vertebra, the logic of anatomy preserved beyond its function. The Megalodon's skeleton, made of cartilage rather than bone, left little behind. What we know of its form comes mostly from the teeth, and the rare, fossilized vertebral columns that reveal its size and proportions. The rest is deduction, comparisons with living sharks, measurements scaled upward, models reconstructed from fragments. What emerges is a portrait both immense and incomplete, a body too large to be fully grasped, a presence too vast to be restored. Science offers the outlines, imagination fills the space between. When paleontologists examine a megalodon tooth under light, they see not just a predator, but a vanished ecosystem. The temperature of the ocean encoded in the isotopes, the chemistry of ancient water locked inside the enamel. Each tooth is a data point in a history of climate, migration and extinction. The shark itself may be gone, but through its remains the ocean still speaks. The living sharks that survive today are the echoes of that age. They are smaller, faster and more specialized, but in them the blueprint of the giant persists. The great white, slender and silver carries the same design of tooth, the same hunting strategy of ambush from below. The tiger shark, with its wide head and slow, deliberate motion, echoes the patience of the megalodon's approach. Even the gentle whale shark, a filter feeder that lives in peace with plankton, carries the body plan perfected by millions of years of evolution. Every modern shark, from the reef dwellers to the deep water hunters, is a sentence in the same ongoing story. Evolution did not erase the megalodon, it edited it. refining what could survive when the warmth faded. The ocean that remains still bears the marks of the age that came before. The coral reefs, though diminished, still build their slow cities of calcium. The whales that once fled from the Megalodon now glide unthreatened through the deep, their songs travelling the same corridors of sound that once betrayed their presence. The smaller sharks move along the same routes of migration, guided by the same magnetic pull that shaped their ancestors. The planet itself has changed, the continents shifted, the ice come and gone, yet the pattern of life in the sea endures. It is quieter now, leaner, but it still moves to the same pulse. If you could stand on the seafloor where the Megalodon once swam, the world would not feel empty. The water would still shimmer with fish, the sand ripple with crabs, the whales still pass overhead. The giant is gone, but the space it occupied has not vanished. It has simply been filled with smaller lives. The sea remembers in form rather than figure. It recreates the balance again and again, using whatever material the age provides. Every predator that hunts now, every migration that repeats each year, is part of the same equation that once gave rise to the giant. The ocean does not forget, it recalculates. The fascination humans hold for the Megalodon speaks less to its size than to what it represents. It is the embodiment of mystery scaled into reality, proof that the Earth once allowed for life so immense that it verges on myth. Its extinction feels personal because it represents something we recognize in ourselves, the limits of dominance. The shark ruled an ocean that seemed endless, yet it vanished quietly when the rules of the world shifted. Its fate is a reminder that power is temporary, that even the greatest creatures depend on the balance of forces they cannot control. We see its teeth in museums and on the shelves of collectors, and feel both awe and melancholy, as though we've found the shadow of a god. In the living ocean, the traces continue in subtler ways. The migration of whales across hemispheres, the coordination of orcas hunting in packs, the presence of sharks gliding silently through the deep. Each of these behaviours carries an echo of the ancient dynamic between hunter and prey, the fear responses of marine mammals, their herding behaviours, and their avoidance of certain coastal regions can be traced, in part, to evolutionary memories forged in the age of the Megalodon. Even after millions of years, the ocean holds on to its habits. The rhythm of pursuit and escape remains imprinted in its fabric. For humans, the Megalodon exists now as both scientific fact and legend. It occupies that rare space where knowledge and imagination overlap perfectly. Its size has been measured, its age has been calculated, yet it continues to inspire speculation and wonder, fueled by the deep's endless ability to hide secrets. The ocean still covers more than 2/3 of the planet, and much of it remains unexplored. Every year, stories surface of massive shadows beneath boats, of teeth found where they should not be, of the feeling that something vast still moves beneath the surface. Rationally, we know the giant is gone, but emotionally, we remain its descendants, drawn to what we cannot see. The persistence of its myth speaks to a truth about the sea itself. The ocean is not just a physical environment, it is a mirror for the imagination. It reflects our curiosity, our fear, our longing for something larger than ourselves. The Megalodon in its time was simply an apex predator fulfilling an ecological role. But in our time, it has become a symbol, a reminder of nature's capacity for both creation and erasure. Its story endures because it connects us to a version of the world where limits seemed irrelevant, where life expanded without hesitation. If the Megalodon could somehow return and swim through the modern ocean, it would find a world both familiar and foreign. The water would feel colder, the currents narrower, the prey smaller, but the shapes would be recognizable. The same currents would guide it. The same physics would hold it aloft. The same patterns of motion would still govern the sea. It would glide through schools of fish that scatter in instinctive panic, unaware that they were looking at their own distant history moving among them. The ocean would receive it without resistance, because the ocean never resists. It absorbs, adapts, and continues. The fossils remain, but they are not relics of tragedy. They are reminders of continuity. Each one is a message from a world that did not fail, but changed. The teeth, embedded in rock, mark the threshold between eras. They tell us that every rise carries its own decline, that every abundance carries its own correction. The Megalodon lived because the world was warm and generous. It died because the world evolved. Both truths are equally magnificent. When you imagine that ancient sea now, the coral coasts, the migrating whales, the silent shadow of the shark beneath the light, you can almost feel the rhythm of the planet's older heartbeat. The sound is slower, deeper, steadier. The warmth presses close, and the water moves with the patience of eternity. The Megalodon glides through that blue expanse unhurried, weightless, unaware of time, carrying within it the perfect balance of power and peace. Then, as the ages shift and the water cools, it fades, not in suffering but in completion, as though returning something it had borrowed. The ocean closes over it and goes on breathing. The deep still holds its memory. Somewhere beneath the layers of sediment, its teeth lie buried among the remains of the whales it once hunted, all equal now in the same stillness. Above them, the living ocean continues its cycle. Sharks still prowl the reefs. Whales still sing through the depths. The sunlight still glitters on the surface. Nothing is missing, only transformed. And as the waves move against the shore, you can imagine the echo of that ancient rhythm returning. The sea, eternal and patient, still remembers its giants. The fossil in your hand is proof that it once dreamed on a larger scale. So you listened, not for sound, but for presence, and realize that the ocean is still whispering its story. The Megalodon is gone, but the water it swam in never left. It waits, infinite as ever, beneath the moonlight, carrying both memory and silence in equal measure. And if you close your eyes long enough, you can almost feel it there. The pulse of the ancient sea, still breathing somewhere below, still moving, still alive.